Okay, everybody, come back for me at 1 p.m. EST. I don't know where that covers, but I am in Michigan. So 1 p.m. in Michigan time or wherever else that same time zone exists. Well, before that, I'm not going to explain anything, right? So before 1 p.m., I'm just going to try to crunch some stuff out here. I'll keep my screen visible so you can see what I'm up to, but it's not going to be that exciting. So I would say if you stumble upon this stream, I would go check out Don Ho at 5 a.m. and Hirose at 8 a.m. Don Ho does C code and works on a engine he calls the Keck engine, and at 8 a.m. Hirose, he works on a UI library that has 0 dependencies. You do have to use OpenGL with it, I believe. I think it might have another way to use it as well, but I was looking through the code. It looks like it has an OpenGL backend that you have to wire up. But both of them do C code. So Don Ho does C code at 5 a.m. and Hirose does C code at 8 a.m. usually. Me, I'm all over the place, but I try to do this at 1 p.m. usually on Mondays. But my sleep schedule is all messed up. I'm like, I'm going to try to get to sleep, and then I'm just going to waste a whole bunch of time, so I'm just going to start coding now. But I'm not going to actually explain much of what I'm doing. Most of this is just going to be unit test code, but once I'm at like 1 p.m., I'll kind of like explain, or if somebody throws people my way, I will also kind of explain what I'm up to. But for now, I'm going to, like if you look at Hirose here, sorry, I almost said Don Ho, but Hirose here, and then if you look at Don Ho, right, so 8 a.m. on Monday, and then if we look at Don Ho, I believe they're all at 5 a.m. I don't know how he gets up, like, so ridiculously early, that's inhuman, but if you look at their schedule, yeah, Monday, 5 a.m. So anyways,
hey, welcome.
I'm just going to, okay, so I'm just going to make a post here on LinkedIn, and then I'm going to go to my dashboard, and we're going to get going. But like I said, I'm not really going to explain anything. Right now, I just want to fix up some code and some unit test code, and it's not going to be a fun time. So I just want to get this working. Oh, also, I'm going to use my other browser, so Torch browser. I try to keep the Torch browser for Twitch, and then I use Chrome for things that are not actually work-related, so that way I don't have to nuke my search history, if you get my drift. Even though I'm sure that there's, if you pay attention to my autocomplete on screen, you'll probably see things that I should sanitize, but oh well. I'm human. Anyways, okay, just gonna put this up here. We are on, let's see, what stream number are we on here? We are on stream number 105. So let's change this to 105 and fix those unit tests. So right now, we just need to fix those unit tests. It's number 105, that's all I really care about. I'm gonna put this up here so I can see it if anyone's looking. But yeah, I'm not really going to explain things. I recommend that until 1 p.m. you check out Don Ho, Hirose, and then me at 1 p.m. because I am just going to try to tie up some loose ends and whatnot, and get my coffee going, listen to some music, and hopefully figure stuff out. But actually, before I start going, I'm going to look for something on Overclocked Remix, find another album, because I've listened to all the OC Remix, I think it's ocremix.org. It's no longer called Overclocked Remix. I've been using this site for like 15 years, on and off. And the domain name has changed since I was first using it. So let's see what we can find in terms of albums. So music, and then albums. I believe I was going to go through all the albums in alphabetical order, so Apex, right, I'm just going to do everything in alphabetical order, so Apex 2013, 2014, so this is the next album I want to take a look at, and as I kind of download this stuff, I do make sure to, if a song has lyrics in it, I will delete that song from my personal archives, because it's just very... It's not conducive to my productivity to have songs that contain lyrics, if that makes sense. So let's see, we'll make a little folder here. You can't see what I'm doing, but trust me, I'm making a folder here. Apex, this is the 2015, so Apex 015. I will not be around by the time we get to 2115, I don't think. Morbid, but that is realistic. So I'm sure we can just name it that way, and that'll be fine. Show in folder. Okay, so let's clean this up. We're going to unzip this. Extract all. Extract. Now, really, I guess I should have got this ready beforehand, but, you know, whatever. So now we're going to delete the zip file, because we've extracted everything. We're going to go in here, and we're just going to cut everything out of here. And it's like, I guess I don't really need the artwork, but this is how I've been organizing all the other folders, where I've just been keeping the artwork and keeping the MP3 folder. Yeah. So we're going to take this, then we're going to open it with VLC. We'll open one of them with VLC, and then once we have opened it in VLC, I'll show you how I do this. Little VLC tutorial here. Pause this. We're going to do open folder, and then we're going to go find this thing that we just unzipped. So it's in Apex 2015. We're going to open the MP3 folder. Unfortunately, when we do that, we have duplicates here, like this here and this here. Here is the same thing now. So it's kind of a hackish way, but really I should just open up VLC and do that. Or could we clear the playlist? Can we clear this? Oh, clear playlist, media, open folder. Let's do that again. So this thing right here, open that. There we go. Okay, cool. So I'm going to listen to some music, try to get some code going here, try to be productive. Also, before I do that, I know I'm all over the place here, but I remember a quote about just stared at a blank piece of paper. I want to find that for a second. Just stared at a blank piece of paper. And it's a quote. Piece of paper. We're going to get kind of depressing when I find this. Blank paper. Paper. Blank. Blank math, math blank, paper math paper. Well, that might actually be something already. Okay. I just stared. Stared at. How about that? Stared at. Okay. So, let's see if we can find this. See if we look for the keyword meth in my shortcuts. We're taking this to a dark place. Legal meth. So World War II. I was looking at a thing where they took like World War II rations from the Allied forces, and they have like these energy pills they take, which is basically like meth. And then I somehow from there I got into looking at a like, you know, the role of drugs during World War II, and then I also found this mathematician quote. So I'm going to take this, and I'm going to put this over here, edit file, and then I'm also going to reload my shortcuts, right? So I'm going to take all these shortcuts, and I'm going to reload them, so that everything's kind of fresh, and then I'll actually be getting down to business. Alright, so it takes a little while to get situated. That's why, you know, when you talk about context switching in Scrum methodology. This is what they're talking about, where it takes a little bit of time to get situated, right? So let's see. I got some shortcuts I need to remove collisions with. So let's see what we got here. We got who killed JFK. Who killed JFK? Which supposedly we know who killed JFK already. Howard Hunt supposedly is the one who killed JFK, according to his deathbed confession, and no one batted an eye. It wasn't big news. I don't know how true that is, but you know, I think you know, usually when people have deathbed confessions, they're, you know, being truthful, but you know, whatever. Who knows? So let's say who killed JFK. So this thing here is the same URL here. So let's say take this out of here for a second. And I just want to get this, like, I'm not going to clean up these shortcuts too much, right? I just want to remove any collisions, right? So if this is already used, I want to make sure that it's not used anywhere else. So deathbed JFK, JFK confessions, JFK killed JFK, killed JFK, JFK who, how about who JFK? Let's not do that. Let's just kind of get this working, right? How the CIA assassinates people, a lot of fun stuff. So printf hex for places. So that looks like it's already been used. We're gonna take this, we're gonna cut this, and we're gonna go find the newer shortcut just so that it's in the same place. Okay, printf hex to 4 places is this. So let's just take this. And is this also the same as something else? Doesn't look like it is. We'll just take this and say, we'll make an underscore version of this. Printf hex for places. Printf hex for digits. Okay. So there's a lot of redundancy in my shortcuts. They're not the best organized thing. It's really like a brute force thing of just make more shortcuts, more shortcuts, more shortcuts, and eventually we have a nice little knowledge base. Also, do you like my webcam? Look, that's me. I'm totally here. I'm totally here. You can kind of see me back there. Now, I really don't have enough room for a, oh look, I got my stripes. I don't really have enough room for a face cam. The most important thing for this stream is to document the code I'm working on. And we can't really document the code if my face is taking up all that room, right? So the purpose of opinions. So 15,000 versus this new one. The reason for opinion, the purpose of opinions. We'll just take this thing that says the purpose of opinions. We'll remove that, and because we kind of promoted it or duplicated it here, that's fine. And let's rerun this. So the purpose of opinions is to make people like you. According to Joska Bach. And he says there's really no situation in which it is advantageous to be in disagreement with your boss. So, unless you're very much a nerd, then your opinions on everything are probably based on just the opinions of the people you side with, right? So, if you wonder, like, why masks somehow got political, right? Because masks should be like a cut and dry science thing, right? Where, you know, masks reduce the probability of you being exposed to or exposing someone else to viral payloads, right? Especially since COVID seems to travel by little droplets in the air, right? And this isn't anything new, right? The panic of what do you call it? The Spanish flu of what was it, 1915 or something, right? I was watching some documentaries on this Spanish flu. They also recommended people wore masks, and I think a similar thing happened with people refusing to wear masks and whatnot, but somehow it got turned political. And I get the libertarian argument of, well, you don't want to be forced to wear masks, and I totally understand, like, not wanting to be forced to do something. But I feel like it might be weird, but I feel like you could protest being forced to wear masks, but still wear masks while you're protesting that, right? Because they're still a good idea, but I get the idea of not being forced to do it. Like, just because something is a good idea, I totally get why you would be against, like, the authoritarianness of, like, forcing somebody to do that just because it's a good idea. Like, don't do it because people are forcing you to do it. Do it because it's the smart thing to do, right? So, like, I don't wear a mask. I don't wear a mask out in public because people force me to, or because the business says that you have to. I do it because it's a good idea, right? And so I think it just politically, it created this weird thing where, I don't know, it just got out of hand, but I try not to get too political on this channel because I don't want to cancel myself or say anything too stupid. And if you have ever read Robert Greene's 48 Laws of Power, the more you talk, the higher the probability of you saying something really stupid to get yourself in trouble, right? If I to exaggerate, or not to exaggerate, but let's say during this stream, I say something that is far left, and then later I say something that's far right. What do you think happens to me? Well, now the far right and the far left hate me. And then I say something that offends the left, and then I say something that offends the right. Now everyone hates me, right? Like, when you say things of a political nature, you really, for the most part, people respond in a greater magnitude when things are negative. So when you talk politics, you really only are, in my opinion, you're only eliminating. You're not making alliances. You're just making enemies, right? So if you think for yourself, then you probably have opinions. Then some of your opinions are probably considered leftist, and some of your opinions are probably considered rightist, right? Like if you're actually thinking for yourself and not, like, towing a party line, you probably have opinions that cross the political spectrum, depending on what they are. And so that means that you're going to cause trouble for yourself if you keep on talking like me. Unfortunately, I have a habit of not shutting my mouth. So I should just mute my mic right now. EB Synth. Why is this another shortcut? EB Synth. How I make my videos. EB Synth. So I'm just gonna say EB Synth Kitten. And then over here, EB Synth, Joel. EB Synth. So EB Synth is, I guess, there's like this new guy on YouTube called Joe Haver. I don't know how to pronounce it, but he's making these videos using, like, AI assisted rotoscoping. And I was really curious as to how he was doing that, so he actually did a tutorial on how he makes his videos. And one of the keys is EB Synth, so I just want to make a note here. So it looks like I had previous shortcuts for EB Synth, so I just want to make a note of EB Synth Joel and EB Synth Kitten, because it looks like I made a old entry, like a very old entry, because this looks like back when I had a 50 character column limit. Right now I use a 64 column limit. So let's reload this. It's going to take me a long time to get here. Yeah. So I don't know. Anyways. So, on this channel, I really would like to say that people really can say whatever they want to say. And if they say something that's stupid, that I disagree with, well, then I can tell them that they're stupid and I disagree with. But I'd also like people on this channel to be respectful to my interest of not wanting to get myself canceled. So, say whatever you want, but don't intentionally offend people, right? Like, if it's just the truth, right? If you're just saying the truth and it's offensive, that's one thing. But if you're actually just trying to offend somebody, that is different. Like, I had an ex-girlfriend who I said I never wanted to ever see again, ever in my life, and never speak to them for the rest of my life, and I was serious. And you know what? There's no nice way to say something like that, right? So sometimes you have things to say, and the truth of what you have to say is just harsh, right? And if the truth is harsh, like, I'm not one for tact, right? So if you say the truth in a way that is not softened, that's fine, you know. Like, once upon a time, when I was doing a lot of, like, online dating, like, one of the things I wanted to try was to try to get feedback, right? Like, a lot of times, like, if a date doesn't work out, you get ghosted. And so I tried to learn, how do you get feedback from somebody who ghosts you, right? And so the best way to get feedback from someone who's ghosting you is, well, you cannot come off as threatening, right? Like, nobody wants, like from a female perspective, I think their worst fear is, like, encountering someone who's violent or obsessive or, like, a stalker, right? And if you can assure somebody that you're not violent or obsessive or whatnot, or any of those things, then usually they'll be more than willing to, like, give you feedback, right? Like, if something doesn't work out and you want to get feedback, like, if you approach the situation carefully enough, you can actually get feedback, right? And some of the feedback's gonna hurt, but it can be useful, right? So, like, I think one date I went on, her feedback was like, yeah, your voice is just annoying, right? And now there's nothing I can do about that, right? But it's good feedback, right? Because to know your strengths what your strengths and weaknesses are a good thing. But in order to know your strengths and weaknesses, you have to look at the world as it is, right? So you don't want your ego to cloud your judgment, right? So, like, a lot of the reality is not going to be pleasant about, like, who you are, what you're capable of. Like, maybe you're not as smart as you want to be, but that's just the reality, right? So I know kind of, like, how smart I am, and turns out I'm not smart enough for Vulcan. Hopefully, maybe one day I will be, but I'm not, right? And knowing as I work on this engine, I have to, if I want to actually be successful with this engine, I have to know, how smart am I actually, and what can I code that is within my mental grasp, right? And unbridled positivity culture is just as bad as just being unbridledly negative, right? Like, the idea is to remain as neutral as possible, right? And slanting something, being deludedly positive or deludedly negative, are both kind of, like, bad things, right? So try to look at things as realistically as possible. Not always easy, but try, right? Because the best way to, if you want to do things that are based on reality, you have to have a good touch with reality, right? Anyway, so I think my shortcuts are reloaded. But I'm not sure. Okay, they're not reloaded, but there's no collisions. Oh, god damn it. Here's another collision. Okay, what's this collision? So I'm gonna keep on searching through these shortcuts and ranting, and then recording how long this took, because it's almost a half hour in, and we're still like, legal meth. I'm gonna guess that's in real, street legal meth. Okay, so, I believe street legal meth would probably be, Ritalin. Okay, so... Okay, I need to... Okay, I need to make sure that these... Oh, hey! So right now, I am up way too early. I thought if I went to bed, I thought if I went to bed that I wouldn't be very... I would just roll around in bed and not actually get to sleep. Technically, it's Monday, and so technically today's my coffee day, so I was like, screw it. I know I got up at 9, and it's been a few hours, and so it's kind of dangerous not to be at a completely fresh start as I start, like, mentally. Like, ideally, I want to wake up, drink coffee, and, like, have everything kind of in sync. And so I'm taking my, like, little coffee payload now. So I am kind of ranting to myself. I'm trying to get set up here. But I have a little schedule here. So my recommendation for today is 5 a.m. Don Ho, 8 a.m. Hirosa, and then 1 p.m. coming back to me. That is my recommendation because I'm going to try to keep, once I get everything situated and it's working, I'm going to just kind of keep quiet and listen to some techno until 1 p.m. Just because I don't want to step on the other fellow C streamers that I like. So I have my little, if you look at the bottom left, you can see the little schedule for today. So those are the kind of people I recommend to watch before you come over to my channel. Obviously, I think it's before 5 a.m., so obviously you can't tune into either of them right now. But they've been good to me, so I want to be good to them. Anyways, let me, I am still organizing my shortcuts. So sometimes, you know how I organize things, I want to make sure that I have these shortcuts correct. So, street legal meth is probably Ritalin. Yeah, exactly. Like, I want to be good to the people who have helped me out, right? So to do that, that's why I have the little schedule down there. And I am going to, mute myself once I get this all set up. Unfortunately, I guess it takes a while to get set up because I gotta reload my shortcuts. Then as I'm fixing my shortcuts, I gotta make sure that they're correct. So everything wrong with the system. Yeah, so this is a little documentary about, I don't know if it's just a documentary about meth. Oh no, it's more about, it's not just meth. It's an interesting video. Everything wrong with the system. I'm just gonna put that in chat for you. Yeah. So then I think the other thing I was watching that's also related to methamphetamines was this video. I think this is like war rations, I believe.
Will stimulate.
Yeah. So, right, World War II. Soldiers on the Allied and Axis powers were both like taking basically meth to fight, and I think the Allied forces called them energy tablets, and then I forgot what the Axis powers called them. Like some weird name that started with a P and had a V in it. Putvin, something, I don't know. But anyways, I was looking. I was watching this, and then I started researching like I was thinking about the role of drugs in terms of technology, and I don't know if you know this, but the Enlightenment started when coffee shops started to open up all over the place, and when people switched from coffee shops to bars, everyone drinking coffee instead of alcohol, that is partly attributed to the Enlightenment, right? And that kind of makes sense, right? But yeah, I just want to make sure that. So I'm trying to resolve some of my shortcuts here because. Okay, I think that's good. And as I was watching this, I started, looking on Wikipedia and stuff. And there's like some famous mathematician, he used amphetamines. And there's this quote where he says that for a month he won a bet that he said he like wouldn't do amphetamines for like a whole month. And he won the bet because he didn't do amphetamines for a whole month, but he didn't get anything done for the whole month. And then he said that he proved that he wasn't addicted. And I don't know what his definition of addicted is, because I feel like if you can't get any work done without drugs, that sounds like addicted to me. But maybe he meant in the sense that he had the willpower to not do it. But sometimes I wonder, how. Am I just stuck to where certain levels of productivity are just... I have to have coffee? And I wonder, have I done that to myself, or is it just like a thing where the human brain was never... We were never supposed to program, and we just kind of technology just evolved this way, and now in order to catch up we have to be doing coffee or some other type of drug to mentally comprehend it, or if it's sometimes I wonder if I'm outside of my league, and so I need the coffee to keep up with everybody who's smarter than me. That sounds kind of depressing, but sometimes I wonder. Let's try to refresh this, reload this script. But yeah, so every time I drink coffee, I do think of coffee as a drug, and I do try to take it kind of seriously, when I use it. And I don't know. I think that I don't know what you're putting in your body, and know the consequences of what you're putting in your body, right? And as long as you're an informed adult and you know what the consequences are, then it's all up to you. It's your body, it's your choice. So, but anyways, I'm still reloading my shortcuts. I can't believe this is already 33 minutes in reloading my shortcuts, but sometimes it takes a lot of time, because if it's been a while since I've reloaded all these shortcuts, then there's a lot of collisions, and the further down the file is where those collisions are, the longer it takes to realize that there's a collision. And I used to reload these shortcuts more often. Now I try to do it just once a day, just because there's so much stuff in here that it takes way too long. Eventually I want to make an OpenCL parallel sorting algorithm to do this, but right now I'm just going to have to manage with, resort stuff at the beginning of the day, and then just don't resort it till the next day. And that does mean that for anything that I make, I can't really reference the shortcut until the next day. Not the best workflow. I wish I could have something a little bit better. But you gotta... there's always resistance when you're working, right? There's always, like... there's always something that's not perfect. There's always something that isn't going as smoothly as you would like it. And your job as, somebody who's working in the real world and not a hypothetical world, your job is just to try to cope with how things are and try to minimize the friction that you are incurring, right? So we'll see if I can just keep up ranting until everything's ready to go. Also, the music tracks that I'll be listening to today are, I went on to Overclocked Remix. Let's get on to Overclocked Remix really quick. ocremix.org. Where are you? ocremix.org. So, their albums, I should really make a shortcut for their albums. So, music, I'm going through all their albums alphabetically, and if we look at, so I took this album here, and I downloaded it, so I'm going to be listening to this while I'm coding. So that is what I'll be listening to, and I wonder if I can have room to put that on my stream. I guess technically I kind of have room to put that on my stream. So I think I'm going to do that as well, since I have a little bit of room to kind of put this. See if I have a thing called music URL. I've changed that. This will be, I'm going to rename this. Okay. And text. Okay. Oh boy. Oh boy. Oh god. That is a negative scale, right? Yeah, that's what I did there. Okay, come on. Let's take this. Let's put this over here. Oh, that's not going to be very helpful, is it? It's better than nothing, though. And I'll also, while I'm waiting for this to reload, let's see if we can take this and... Oh, looks like we have another collision. This sucks. And the collision is frog research. I'm gonna guess that has to do with the gay frogs thing we were looking at. I'm gonna take this. I'm gonna go back up to the original link. Frog research, huh? Really, frog research. And that's a TXT. I have no clue why I have a text file called frog research, but I don't even know. I don't know if I was being silly when I made that, because it doesn't look like... The whole file, yeah, it looks like I was being silly when I created this shortcut. I gotta stop being silly like that, because sometimes it collides with something that actually makes sense. But now that we're here, I might as well just kind of fix this. So let's say, pick frog research txt or frog research YT URL. Let's just do that. So I guess supposedly so the whole like Alex Jones gay frogs thing, There is actually some research. I think it's there. This might be a mini documentary on that or something. But it's not gay frogs. It's like chemicals causing frog hermaphroditism. I can't pronounce that correctly. Hermaphroditism. I don't know how to pronounce it, but there is actually like research on what Alex Jones said. But his claims are kind of like hyperbolic and what do you call it? Not quite correct, right? It's almost like a game of telephone. Frog research. Sure, and let's take all of this stuff here. And, oh, it's already there, okay. Okay, let's reload this. So is this going to take me an hour just to get ready? Yeah, I need a better workflow here. I think that maybe next time what I should do is, since reloading my shortcuts takes a long time, maybe I should reload my shortcuts, do some push-ups, check to see if the shortcuts are broken, do more push-ups, check to see if the shortcuts are broken, do more push-ups, etc., etc., etc. And then once the shortcuts are actually in a stable state, then I should start the stream, because this is kind of like wasted chatter kind of on the stream where it's not really, there's no actual coding going on here, it's just me ranting. But while I'm waiting for these shortcuts to kind of reload, let's take the URL for Overclocked Remix here. Let's take that URL. Let's refresh that. So this URL, let's take that tiny URL there, and this is Apex. The album is Apex whatever, but actually I have like URL. I have a naming convention dedicated to URLs, which is YMU for YouTube Music URL. This technically is not YouTube, but I'm just going to keep the same prefix for these shortcuts for music, just to have like a sequential kind of system here. So YMU026. So 27 would be the next one. YMU027. So I'm going to take this album from Overclocked Remix, and I'm just going to say YMU027. See if I can make a tiny URL with that so that I can share it a little bit easier. Make tiny URL, and that was made. Excellent. So I can take this now and put this into my shortcuts, and then I can also so YMU027. Okay, let's take this. And so let's make sure that works. So if we go over here, if we go YMU027, we should be able to get to that album. Cool, so that's the album. So I just want to, while I'm here trying to get everything situated, I might as well make it so that I can credit where credit is due, right? So let's put this right here. So the music is going to be from, so a little music URL. I mean, that's not the most professional layout here for the stream, but the information is the most important thing. The presentation kind of takes a back seat, which is a weird thing to say coming from someone working on a rendering engine, but okay. So now I'm playing the waiting game. So actually, let me look at, while I'm here, why don't I go over the, I just stared at, So, here's the thing I found on Wikipedia. Wikipedia, history and culture of substituted amphetamines. And then in mathematics. In mathematics, perhaps the most notable example of this is Paul Erdos. I don't know how to pronounce that. We'll just call him Paul, because I can't pronounce his last name. In mathematics, perhaps the most notable example of this is Paul, one of the most prolific and successful mathematicians in human history. He took amphetamine and methylphenidate occasionally throughout his early career. He began taking them daily at age 58 when a doctor prescribed them to allay the depression associated with his mother's death. Oh, that's Ritalin? Okay. Okay, got ya, Ritalin, yeah. I know a lot of programmers who do Ritalin. I think my brother does Ritalin. He began taking them daily at age 58 when the doctor prescribed them, and didn't stop until his death at age 83. He would also sustain himself on a copious amount of coffee and caffeine pills. Erdos took amphetamine despite, and I have to reload this, despite the concern of his friends, one of whom, Ron Graham, bet him $500 that he could not stop taking the drug for a month. Erdos won the bet but complained, "You've shown me I'm not an addict, but I didn't get any work done. I'd get up in the morning and just stare at a blank piece of paper. I'd have no ideas, just like an ordinary person. You've set mathematics back a month." Then he promptly resumed his amphetamine use. Yeah, so, like, when you're doing, if you're consuming, like, drugs, like, I don't know, be careful. Like, I feel like I'm kind of somewhat stuck on coffee, to where the days when I'm not drinking coffee, I'm not as productive, right? And so I've kind of chosen to be like, you know what, I'm kind of stuck on coffee, but we can at least kind of mitigate the damage and be like, drink coffee once a week so that it always has an effect, right? We don't need to drink coffee to feel normal, right? If we only drink it once a week, we can use it to get, like, get our brain kind of spinning fast. But the downside of that is other days we're not as motivated. But it's a little bit better than just not drinking any coffee. And yeah, see you later. Have fun at university and all that good stuff. But yeah, I'm gonna keep on talking to myself, even though you're gone, just because I'm just trying to keep my stream of consciousness. But yeah, I will see you around, maybe at 1 p.m., depending on what you have to do. But yeah, I'm just going to keep on trying to reload my shortcuts and get this going here. So, also, I'm going to keep a note of, that you said that was Ritalin, because I didn't know that. And I'll just make a note in my shortcuts about your commentary there. Alright, there we go. Okay. And so we have something called train wreck. We gotta find that. Where are you? Trains wreck. Alright. Trainwreck TV. Oh yeah, because my streamers were, my audience was recommending some people. And Trainwreck TV. Figure out what that is next. And this is... That is an interesting shortcut for Trainwreck. I'll just call it train wreck function, I guess. Also, I have no clue why that shortcut is named that way. But, it's way down there, so we should really put this series of shortcuts up here in case there's collisions so we can find them quicker. And we'll just take what it resolved to. 22,600. Oh, god damn it. Showing my things that I shouldn't be showing. Oh well. I never denied being a heterosexual, so okay. So, but I really should clear my shortcuts like that. I shouldn't. Oh well. Okay, so let's see. That is there. Trains wreck. Trains wreck. Okay. This is from SC 22,000, and I kind of already forgot what the shortcut number for that was. Okay, train wreck. So train wreck. So we have train wreck TV, and then we also have a train wreck funk, and I have no clue what that was originally for, but now it's in my shortcuts, so I can find it. And then before we get this, let's reload this, and let's look through all the bookmarks that we put in our shortcut file and be like, let's see, so what did I expose to everybody? Well, some good shortcuts, but not shortcuts that we want to show people. Okay. Reload this. Let's see what else we got here. Okay, that looks good. Okay. One of these days, I'm gonna get myself in trouble. Okay, so it is almost an hour and still reloading shortcuts. This is probably not the best use of my time. I should probably get stuff open on Wikipedia and start reading it, like if I'm gonna do something like this. Or I don't know. We could look at Facebook. Try not to get ourselves in trouble on Facebook. I'm facing an error. Oh, a C++ C group on, anyone can sort out this issue. Well, it depends. What language is this? Page.statuscode for I in range. Ooh, Python? Screw that. Uh-huh. Let's go look at LinkedIn while we're waiting here. Let's see, notifications. So this guy, I don't know how I stumbled upon this guy. But I think this guy is working on his own game engine. He seems like a pretty competent graphics person. I don't think he has like a Twitch channel or anything. But this person right here, it'd be interesting to see where their stuff kind of goes. But I friended them on LinkedIn. I'm trying to, like, I don't know, use LinkedIn more than I use Facebook, because I mean both of them are kind of time wasters, but I feel like LinkedIn might be a more productive time waster, if that makes sense. But yeah, I am interested to see kind of where their stuff kind of goes. Grand translation. I don't know what that... Oh, they're two different guys. Are these two different guys? Man, they look really... It almost looks like the same person from two different angles. Hold on. Nope, I guess they're two different people. Are they? Same exact facial hair type, glasses, similar haircut. Alright, well, probably shouldn't be commenting on people's appearances here. But yeah, I like to see when people are working on cool stuff, and seeing kind of like stuff like this, I think is more productive than going on Facebook and seeing things that are political. And I think maybe my shortcuts are actually going to reload now. And then it'll have taken an hour to get where we are. So I guess while we're trying to reload our shortcuts, let's think about what needs to happen here. Like, what am I working on now? I know I'm trying to get my my tests passing, so that's the first thing. But what tests specifically am I working on here right now? I know that the bitpacking didn't seem to be working properly. And that's kind of scaring me because I'm wondering, is it the bitpacking that's not working properly, or is it actually that it's not setting the data properly, and the test was a little bit wonky in the way it is running, so there's always the potential that this test is... There's always the potential that this test... that the test code is failing, not because the code is wrong, but because my methodology for how I decided to write this test is completely wrong. So we're going from pixels to bits, and in order to go from the these canvas user pixels to canvas user bits, we actually have to do a lot of transformation, because we have to figure out the we have to go from the canvas user pixels to the to all of the different locations. Yeah, so I kind of get why I'm doing that. But yeah, I really don't want to figure this out right now. But yeah, there was something that I did that was kind of like... We did a put here, and then we went through everything. Right, so paint picks to QV picks, or whatever the heck. So are we testing this function, right? So this function here, and I think we are. Yeah, we have a test function. I believe I wrote this yesterday, and I was pretty happy with it. Yeah, I was pretty happy with this function that I was testing. Right, so this gets the location, which picks might be the wrong thing to call it, because then it kind of sounds like it gets a pixel, but it says pixel here, but these are the locations of the pixels. And I was pretty happy with that. And it looks like we're kind of stringing together this function and this function to create a function that takes pain pix and converts it to cov bits, right? And what are we testing here, though? So we're going from pain pix to whatever. But what are we testing here? What is the test here? So so pixels to bits, right? And it's going from the canvas user location to the bits, right? But then down here, this code kind of suggests, if that's the case, then why is this code kind of saying that we're going paint pixels to whatever the heck, right? This seems kind of backwards-ish. And is that a reason for why things aren't quite working the way they need to work? So we're going through the layer, the tile exponent size, Interesting. I need to take a quick break here. So yeah, I just gotta figure out where the heck does this test make sense? Do these other functions work? Like, why is this loop through again using triple loop instead of quadruple loop and check your outputs against expected values, right? So it looks like, so none of this is canvas user pixels, right? So this is going through paint pixels here. And I can kind of see here. So it's like, why does it say, none of this suggests that it is the transformation that I want. And I don't know why that is, so hold on. Anon-chat. So, yeah, I need to... Anon-chat. I'm just trying to get this thing working here. So it looks like... Okay, that looks good. That looks about good. We're really close to getting these shortcuts reloading, because this collision happened at like line 315,000. So 315K. So I'm pretty sure that I'm very close to getting my, but we're at an hour. So let's kind of keep on looking at this code while we're trying to figure this out. So PAINT5D to CovPix. CovPix to CovBits. And this function, I don't know if it's quite written correctly. Because it says CovPix to CovBits right here, right? But then the transformations don't quite look like that, do they? Because the way I wrote it, right, I wrote this nice little table, but this table here, yeah, this input table is for all these different tile exponents, and yeah, so all these different tile exponents, they're underneath a certain canvas user view pixel. So I get that, and that they need to collapse into these values here, and that's fine. That makes sense. But then the loop, in terms of like what we're going through, we got the test index and we got the layer, and we're going through here. Like, this is worrisome. This is very worrisome that it's not cross-check, simple get put test, right? So this is a get put test. We're going through the test index right here. So, right, like, all that stuff was, like, boilerplate. This is where the actual test starts. We're going through all the tests, and we're going through the tile quadrant and the offset decks, and we're getting like a TX and TY, and then we're putting something. Okay, so I see what we're doing. We're kind of like trying to put using our old put command, and we're trying to like get it to work with the query, right? So, but that's not really what the test name implies, but I get why we're doing that. So we're trying to like put stuff at a certain tile quadrant, tile exponent in a layer, in a certain TX, TY. Okay, sure. And then after that, we're trying to loop through everything and get it. But if we... So we're putting all these values. So here's the test. Here's the main test. And in this main test index, first thing we do is we loop through all the quadrants and the offset dexes, and we put all these values. For a certain quadrant and a certain offset dex, sure, that's fine. Then we go through every layer. But the layer is right here as well, so why is there a layer here? So the indentation is confusing. It seems that this indentation is... Yeah, so this is here, so we're looping through a layer here. And that means this thing will go through the layer, the exponent, and all that stuff. It's going to go through here, and TX, TY equals get the corner thing. And it's the same thing here. And we're going to take the pane pixel, and we're going to try to get the CuviePix, and then from CuviePix we're going to try to get the bits. So there's a lot of like weird indirection in this test, to where it's like, I'm not sure. Like, I hope we can get this working, because we wrote some other tests for it as well. But there should be another function we could write that would make a little bit more sense, right? Where we, like... It might not be a function that we're actually going to use But so this thing here, right? We have so this right here could probably be a this is a getter function, right? It's a converter, but it gets stuff, right? Because it converts to this. It takes this coordinate and it gets out those bits. So I almost feel like, because I wanted to name this as like cuvpix to cuvbits put, and then cuvpix to cuvbits get, right? So there's a symmetrical version of the function. So let's look for this function and just see what kind of files it's in, right? What files is this in? Is it only in this file? If it's only in this file, make it a little bit easier, but let's make sure that this is in one file. And oh, sure, it's not. Notes and diagrams, right? So you see I have this get. So originally I put this get in front of it. And I think underscore get actually makes more sense. Let's close everything. Let's close everything and open it up and see, like, where are you? So, in hack code, it looks like this is the actual function. Notes and diagrams, we don't have to worry about that. Now, what's the difference between this and that? So, right, we have this thing here. Well, this is the actual implementation. This is where it's being tested. And this thing here is another test function, right? So, and these are all getters, right? So, I'm going to rename these functions. And I'm going to say, wherever we find this right now, we're going to replace it with underscore get, right? So find next, replace, and we're going to save that over here. So we thought originally that it was kind of like redundant or stupid to put like the underscore get on it. But now that I'm looking at it in retrospect, having this get actually makes sense because you can also have a put, right? So we take this pixel location and we get the bits that are there using the get. Or we could take this pixel location and combine it with the bits and we could put it, right? And we want to name things kind of symmetrically so that it is a little bit easier to test. So let's take a... So I feel like making a test for this first and putting it before the other tests we wrote might be a good idea because we're losing kind of track of how those tests actually work. So let's kind of run this. And we're going to make a symmetrical test function here. Or sorry, a symmetrical function. Like, as long as we can get this running. Right, so this failed. So if we copy this, right, so that's our test function, and it failed. Okay, cool. So I think that I don't really like this namespace, but we're going to keep with that namespace. And we're going to do if we use a putter function with this, we want to say, hey, return let's just keep it void for now, but I would actually like to say, yeah, let's just keep it void. Let's keep it simple for now. I know we could, like, return something fancy depending on if the value changed or not, but I'm going to take all these values here, and I keep the signature almost the same, right? So I'm going to take all these parameters. Right, so we got to take the canvas user view location, but the canvas user view location cannot specify everything in terms of where we're going in the data structure. We also need to know the layer and the offset dex. And we're going to take that exact same signature, but we're going to add one more thing to it. We're going to say U32, right? So U32, because it's actually going to be a 2-bit value. Right, so this U32 value that gets returned from here, if we look at the output, canvas user view bits, right? So, now do we want to put... Now, when we have an array of bits, it's all of the... It's not the layer, but it specifies the offset dex. So cov bits here. We're going to call it cov bits 16 because there's 16 of them. It's a U32, but there's only 16 of them. And stores tile values for right. So this cov bits 16, right? So we don't supply the offset dex, we just supply like this right, we want a cuvpix to converted to cuv bits, and we're putting. That's a little bit ugly. Is that really how we want to do this? We want this. We want the get and the put to kind of be able to use kind of symmetrically, where we can kind of get these values, right? So we want to be able to get the bits, right? We want to be able to get these bits from this function. And then we want to be able to just put them back, right? So when we want to put them back, we just take the bits, and we keep it on the same layer, but these bits are all going to specify all of these different offset dexes here. So this is a getter. This is a getter that gets a package of all of the different tiles that are underneath a pixel. And so this needs to be, the symmetrical version needs to specify all of the different tiles that are to be put underneath that pixel, right? So the symmetrical version of the function would be like this, right? So this is the symmetrical version of the function that we want to do, right? So we want a test for this. Cov bits 16. And stores the tile values for osdex, whatever the heck, right? So we have this thing here. And let's go say that, hey, we want to test out the put get thing, right? So let's go look at our functions here and say that so in our test functions, this thing needs to be renamed, right? So we need to rename this thing here to a get, right? So originally this was a getter, right? So we want to take this name here. We want to replace it with as get, right? We want to underscore get on that. So this thing, we're going to replace that with get. That already has a get in front of it. So that looks good there. And before we run this test here, so let's make a note here. So the time is 1 hour, 20 minutes, and 13 seconds. And we just want to make a note that, test sure, why not keep, well, why not just make a whole bunch of ands? Sure, why not? And tests are confusing as hell. Let's, run a So, right now, I think that the tests for QV picks to QV bits, the test code for that is, like, it's really hairy to the point where it's like, I don't know if, I am uncertain if that logic is correct for how we're testing it. Like, I've lost track of it to the point where I'm looking at the test code, and it's like, when the test fails, I'm not even sure if the test is wrong or what, because it's like, when I look at it, I'm just like, I can't wrap my head around that test code anymore. And because of that, this test and this test, I think I actually want to do a putter test first, right? So, do the put test before these getter tests. All right, so I'm going to make a little note of this section here. Right? And I'm just going to kind of label it like this. And everything is horrible. Everything is, like, this is a mess. It's an absolute mess. Right, but we want to say that we want to do these, we want to do the put test before this, right? Now this test here, pain picks to QV picks, we can do that. So right here, I'm going to say, like, do the getter tests before the put tests. Or actually, this is the, do the put test. This is the get test. So we want to do the put test. Sorry. Do first. So the put tests are what we want to do first. Right? And yeah, that is, this is a mess. But yeah, this thing called whatever the heck, blah, blah, blah. We need an appropriately named function that instead of this, it is a put, right? And then, right? And extern void, take this function name, right? And that's ugly. And I don't think we actually have this function yet. Or do we? We haven't actually written this yet. So let's put this somewhere. Let's just put it on the outside of this. This is the main unit test function. I think it would be nice to actually know where this section ends and begins. So this is the end of the function. I would like to... Yeah, because we're running out of room here. Do I have something on the clipboard? No, that should be what's on the clipboard. Well, now it is. So yeah, this thing, we want to test for this. Yeah. Alright, so we want to do this test first. And right now, let's do a log to know that we're inside of it. Let's take this and just say, mark this as begin. And then mark another one as the end of the function. And we'll put everything in the middle of here, including like our macros and whatnot. Right. Okay, so we'll put all the logic here for now. But we want to make sure we can get this running first. So, okay, so we have the unit test code ready to go. And I feel like writing unit test code for here, we need to cover all of the corners like we are in the other test code, because the test code was working until we did those extreme corners. So we're worried that those extreme corners is causing a problem. And so this is what we want to use. And the put command, the way we're going to test it is we're going to test it with the get command, I believe. Is that how we're going to do it? We're just going to use the put and the get and just make sure that it puts and gets correctly? Or are we going to make sure that the... if we're going to test out the put, we should probably test it out in isolation and make sure it works correctly. So I'm actually going to call this let's just make a note, right? So, this function should test that things were put properly by using by clicking at the underlying data, and not by using the corresponding get function. Later, we will want to test a Right, so this first test, we just want to make sure that everything looks correct on the data. Right, so we're not actually going to... We are not actually going to... I don't know where to put this comment. Let's put the log, like, right here. I feel like that's a little bit more symmetrical. Yeah, so for this test here, we're going to test out the putter. We just want to actually look at the underlying data and make sure that the underlying data set looks correct, right? So for that, we're going to have to... we need to clear the entire data set first, right? So our test code should already back up stuff, so we can kind of mess with the data as we kind of feel like. So PAINT5D.data. Actually, no. PAINT5D's actual data, like the actual data for it, is in pixname, right? We've kind of like taken the big data segments and consolidated them into one place, which is a little bit confusing. Is there a note for that here? Did we have a note at the top? Yeah, so in PAINT5D's data, we have like a CPU side bitmap is here, texture location. So we have a note for where that is. So if you look in here to find that data, right, which is a reasonable place to look for the data at first, you'll be kind of redirected there. But let's just say that, you know, for I equals, or int32 I equals 0, I is less than or equal to 512 times 512 times 4, and then a minus 1. Right, so go through every single byte. And right. And we could also do a correct cast, so U08, right? So U08 cast. Get a fresh canvas to start working on. So I would like to use the putter in such a way that we get like a very, that we get some type of pattern that we could actually print out, that we could actually save to the console, save to the file system, right? We could save the PNG to the file system. Let's try to test this in such a way that we can export the texture memory CPU side bitmap to a PNG file and visually analyze it to see where we went wrong. This will require thinking about how to draw a pattern using this putter function, right? So let's think about how to draw a pattern using this putter function and draw a pattern that we can kind of verify visually, right? So that's what we're going to try to do. And the time is 1 hour, 34 minutes, and 2 seconds. So we're going to try to draw some type of visual pattern using this test function, right? I want to make it absolutely obvious that the commentary block that I'm writing goes to this kind of loop in a way, right? It doesn't exactly go to all this loop, but we want to make a note of that, right? So when we're trying to, so we're going to erase all this, and we're going to try to draw some type of pattern here, right? And we're going to use this function right here to draw that pattern, right? And when we draw that pattern, what we want is that if we look in our mod folder, right, we have this thing here, right? And if we look at it, it has a very obvious pattern. So what I would like to do is draw a pattern similar to this using our unit test code and save this to disk, and then we can look at the resulting image and see if the image kind of makes sense, right? So we can set a whole bunch of, we can go around the borders like this, right? And just set, if we can go around the borders and set tiles so that we can get this pattern, right? We are going to use the canvas user view to set tile values to hopefully generate this kind of pattern, right? Now, one of the problems is that as we do that, we have to think about converting kind of a pixel coordinate to the certain tile coordinates. So this is going to take some time to figure out. And also we have to write the code here. So we got to write the code here. So here we're going to put a little error finish this function. And let's put an error. Actually, this needs to be lowercase. Finish this test function, right? So finish this test function. This is also going to say finish this OpenGL function, right? Okay, so we got these two errors here. We just want to make sure that we can get some basic stuff kind of working, that the compiler is going to catch us at this specific moment in time. And then we'll just, we just want to make sure that we don't have any weird syntax errors. So it says error finish this function. And this GL function. So let's do some defines here. So define, right, let's take, all these. So this and this will be IX, cov IX, cov IY. This will be the layer deck, so let's define this as, that sure looks weird. I feel like LaDex had a different shorthand for it than LD. Oh, it's like tile layer, I think. But sure. Let's just call it layer. Just because this seems more easy to think about. And then, alright, let's say B16 for, there's bits and there's 16 of them. Alright, just make these kind of things so that we can work with this in a more terse fashion. And then we'll undef them when we're done with them. Also, yeah, let's just do that. Let's do it like that. Let's make some checksums over here as well. So, okay, so 1, 2, 3, 4, right? Because we need to be indented. This is going to be pasted into some shader code. So we need to indent a little bit more because we're going to surround this with double quotes to make a big string later. So we need to indent that properly. And right now we're just going to do like a no-op, right? So if IX and just do like no-op on the X, Y, and Z. And this doesn't return anything. Yeah, this does a put, but it puts it on the actual data structure, so that's fine. And then over here, we do need to finish this, but for right now, let's just leave it kind of blank, right? Let's leave this test function blank, just to make sure that we can get things compiling first, right? We don't want any, like, weird syntax errors before we start compiling, right? Like stuff like this. And that is from here, right? We need to kind of, like, go in here and go like that. Okay, yeah, let's give that a shot now, right? We just want to get this compiling first. And then we'll just start writing the test code. And we're going to try to use the test code to generate some type of pattern that we can kind of visualize in the resulting PNG file, right? So failed, so this is failing, that's fine. And we're going to run this code before, right? So we're going to run this code before the test that's failing and see if maybe we can fix some code so that the other test just runs and works properly. And hopefully the error... What I'm hoping is that crazy convoluted test code, that the test code is actually written properly and the error is actually in the function that's being tested. That's what I'm hoping for. And that's why I'm going to write another test function to be like, that other test code, it's getting out of hand. We need to write some more simpler tests. So right now, if we look at our logs, we should be able to find cuvpix to cuvbits put, right? So we should see, yeah, so we see this put function, and we're testing it before we test this thing that is failing on us, right? So we can write this code and hopefully get a failure here and fix some code before we get to that other test code that's kind of failing us, right? So I'm gonna be back in a little bit, but I'm gonna start like listening to music and whatnot and doing this. But I need to take a bathroom break here, so let's do break. I'll be back. I'm gonna give myself just 10 minutes here. Okay, hold on. As I was taking my bathroom break, I realized that the signature for the function I want to test might not be correct. But now that I'm thinking about it, when we're putting something... Yeah, so the, I thought that we needed to not use this, but when we use our getter, right, so the output is here, right, because we're writing it in a OpenGL friendly way. This offset dex actually also has to be applied. So we took that off of the signature of this function here, but it doesn't store values for the different offsets, right? The 16 values are not... The 16 values we're talking about are actually all the different layers, right? Because there's 3 layers. So if we look at this signature, so specifies oh, so actually we need to keep the latex as well. So actually, it needs to be all these things. This is latex. So actually, latex and ostex, those actually need to be latex and ostex. Those actually need to be supplied, right? The only difference is the put function has this extra parameter here, right? But the put and get function need to be exactly the same. First 4 parameters, except the putter needs to specify what's going to be put, right? So we're going to target a certain layer, and for a certain layer, we're going to say here are all the different, for a certain layer, and for a certain tile set that we're working on, we're going to say here's all the different tiles that we want to put underneath that pixel, right? So it's kind of a convoluted operation that I don't really expect to ever really need to use. But it's something that I don't expect to ever have to use it like this, but it's necessary to have it if we're going to kind of like test stuff, right? So that's the signature we need for writing kind of like good tests. So sometimes you're going to write code just to make sure that you can test your code. So we're writing kind of like these symmetrical functions just so that we can test the some of these codes here. Store tile values. Stores 8 tiles. Right? This stores 8 tile values, right? So there's 16 bits, but it stores 8 tile values for the different tile sizes, right? So Yeah, I mean, that's good for me. But yeah, I did not plan this out very well. But yeah, so thinking about this, and let's go into the mod folder here for a second. So what do we want to do for a test? I'm thinking that we do a test that puts that when it does the put, it will put in a way that this first cell is going to be like red. This will be green, this will be blue, red, green, blue, red, green, blue, right? It'll do it in that order. Or it could do... I'm thinking red, green, blue, red, green, blue, red, green, blue, then like cyan, yellow, magenta, whatever, and have like 4 different colors, right? So I have 4 different color schemes of 3 colors for these different quadrants. That way we can visually verify it as well as verify it in the code, right? So we can save it to the file system and actually verify that it looks correct, right? So let's try that, right? So in this kind of code here, this put function, we still have to write the put function, but here, what we can do is, let's take this put function, right? And we're going to want to run this put function for the first thing we're going to want to do is run this put function on the on just the alpha, right? So that we can get these like black lines. Or run it around the borders. So here's what we're gonna do. We're gonna say so when we're talking about the canvas user view, we want to go through here. And we want to surround the border. We're going to say the canvas user view IX. Yeah, I want to draw around these borders. Okay, so I'm going to start the music and just try to think this out. Yeah. Okay, pause here. So what I'm doing right now is I'm making this cov box type, and it's actually just going to store a cov ix, cov iy value. We already have a thing called cuvipix, which has the exact same member names. And the only reason this struct exists is to help make the code a little bit more readable, because the data here specifically represents a pixel that is, like if you look at this, it's going to represent a pixel that's somewhere around here like this, but not quite like that. It's actually going to represent drawing pixels around, let's close this. Like when we are drawing, we're going to draw like pixels around this border, we're going to draw pixels around this border, we're going to draw pixels around this border, we're going to draw pixels around this border, and that's going to be cov box 4, right? Because it's going to be 4 boxes that are kind of outlined here, right? So cov box 4 is just going to be stands for these 4 boxes, right? Index 2031 is how many different index values we need in order to trace around here, trace around here, trace around here, and get all the different values, right? Because this is 128, so in order to surround all 4 of these edges, we got to go 0 to 120. 6, right? Because we don't want to hit the last pixel, because the last that last pixel will be used for this line. We don't want to hit the last pixel here because it'll be used for this line, etc., etc., right? Because we need this kind of folding pattern, and we don't want to overlap these vertices here, right? So if we check our math again, we could say, you know, each side is 128 times 4, but then we need to minus 4 because of these shared vertices, right? So the vertices are going to be duplicated, right? So if we take that and we multiply like that, we get a 508. And if we take 508 for 4 boxes, and we 508 times 4, we get 2032 for the total values. 2032. Now we have to remember that we start counting at 0, so 2031 is the total indexes that we need for this. So, with that said, this data structure is kind of a duplicate data structure, and it's just named this way to help us know exactly what the data is used for. So usually I say if the data means the exact same thing, then it needs the exact same variable name. But this is kind of like honing in on this. This is like covbox4 is a, if we want to think about it, let's look for cuv. Let's put some breakpoints here for a second. So cuvpix, right? If we look for cuvpix, we should be able to find a cuvpix type, right? Somewhere in here, we should be able to find like the actual type for cuvpix, shouldn't we? I know you're in here somewhere. Yeah, so this struct right here, right? So this is going to be, so let's make a note here. So vid iid time. Let's just call it 22, right? Covbox for type is just a type with a more specific usage. Top left. Right, so covbox4 type is actually a specific use case of cuvpix. So a covbox4 type is a cuvpix, but a cuvpix is not necessarily a covbox4. Is kind of what I mean here. So let's just try to say for this type, I'm assuming that I'm not actually going to use this. This is a very redundant type. I'm assuming that I'm not going to actually use it in the OpenGL shader, so we're not going to give it this OpenGL namespace. We're just going to say AAC 2020, and we're going to say P5D 1OGL, and the type is covbox4, right? So that is a pretty beefy kind of name there for this stuff, but that should do for what we need to do here. So this is getting kind of chaotic, but right, there is a reason for why everything's named the way we want to name it, right? So let's clean this up a bit, and then let's kind of keep on. Right, so it's like we got two variables here, and then we have like big blocks of code, but that's kind of how I do it a lot, so that is fine.
Yeah!
Okay, let's talk about this right here. So 508 is the total number of pixels for a box that surrounds either this top left rectangle, the top right, the bottom left, or the bottom right rectangle in the canvas user view. So we're talking about this view here that Josh is going to be using. This is 256 by 256. Each one of these sub-rectangles is 128 by 128. And to do like a one-line outline this area, it needs to be a box that's 128 by 128. And this is a box that's 128 by 128. And for a 128 box, in terms of data points, we need 128 minus 1 times 4 data points to outline this continuously from start to finish without any overlapping pixels. And so that's what the 508 stands for. The 508 is the total number of data points to completely encompass this. Then we need to multiply that by 4 to get everything. So 128 times 4 to encompass this, and that's going to be that 508. And then if we take 508 times 4, that should give us one box. So this actually doesn't quite make sense. This 128 here should actually be for one edge. So now that we're kind of checking our math here, we realize that we've been kind of stupid here. So this one box should be 128 minus 1 times 4. That's one box. Oh, no, that's times 4, so that's one box worth, right? And this 508 is also one box worth, right? So assert 508 equals one box, right? So this is one box worth of data points. This 508 is just one box worth of data points. One edge is going to equal, so assert that when we take one edge is just going to be 127, right? And the reason why it's going to be 127 data points instead of 128 is because we don't want any overlap, right? So they're shared corners, and that's why one edge is 127 and not 128. So we could also put that there as well. So assert that one edge is equal to 127. So the number of pixels in one box, the number of pixels in one edge, right? So we have these asserts so we can keep track of what the heck we're doing. Because the potential for being off by 1 is very great with these calculations. So we need to be very careful about this. So let me look at my chat here. Okay, yeah. So yeah, we need to make absolutely sure that we're sane here. And then we're also going to make sure that this dex is within the proper range, right? That when we're remapping this index, that we have selected the correct case. So one box worth of pixels, we need to be less than the number of pixels in a single box in order for the index to map for the first box, right? Because the index starts counting at 0, all right? So these values are the origins, right? So this is the origin of the first box up here, which we've already highlighted. This right here is the origin of this box here. This right here is the origin of this box here. This is the origin of this box here, right? We're going through the boxes in that order. And then the index mapping, right? We just need to subtract the correct amount, right? So if we are here, we're subtracting 0 times one box. We're not subtracting anything. Here we're subtracting the previous box, subtracting the previous 2 boxes, subtracting the previous 3 boxes because we're on the 4th box, right? So these numbers that are counting down should actually be like 4. They should be sequential: 4, 3, 3, 2, 2, 1, 1, 0, right? So you can see that there's this sequential, continuous kind of counting pattern going on here. So if we didn't get that quite correct, then our assert will help catch any mistakes in that logic. Now, when we're going through these indexes here, we need to make sure that this is one edge worth of pixels. So again, we need, instead of less than or equal to, we should probably be, we should probably just be less than, right? So if we're less than 1 edge worth of pixels, we're on that first edge, right? If we're less than 2 edges worth of pixels, then we're on the second edge. If we're less than 3 edges worth of pixels, we're on the third edge. If we're less than 4 edges worth of pixels, we're on the fourth edge, right? And then else, we're out of bounds, right? Air, and we'll just say the base dex out of bounds, right? So the base dex is out of bounds in this case. And there's another assert we can do where, right, we can also assume that we can do something like this for the different boxes here as well, right? We can check our math as well and say that the base dex, what are we expecting the base dex to actually be? Well, for the first thing, we're expecting it to be, we need, the base index needs to be 128. This is the amount of pixels in an edge. And we're going to do times 0. We're going to try to keep the same pattern, right? Right, so 128 times 0 plus 0, because the first index is going to start at 0. Its last index is going to be 128 times 1 minus 1, right? So it's going to go 0 to 127 is going to be 0 to 127. Actually, it is number of pixels in a single edge is not 128, right? The number of pixels in a single edge is actually 127, right? Because of the non-shared vertex, right? So if we're between 0 to 126, right? Because once we get to 0, once we're on the 127th, we're actually on the next vertice, right? So it's actually this, right? So that's actually, this is why it's kind of tricky, and that's why we need these asserts, because to get off by 1, it's going to be really easy to get off by 1 if we're not careful. So we're going to add these asserts just to make sure that we know what we're doing, right? So this will be 1 and 2. And we'll just take these, kind of cut and paste them. Alright, so down here we'll paste this. Down here we'll paste this. 1, 2. 2, 3. 3, 4. So this is the second box. Oh, actually, these are not the boxes now. These are the edges. Right. So this kind of sucks, right? We're adding all this extra code just so that we can write test, right? And that's the thing that's kind of like making us in kind of like this unit test hell, where it's like test and test and test. And I hope that eventually we'll escape this, but for now, the base index. So for the first edge, we're going to start at IX, and the index is whatever this base index value is, right? So we're going to travel around this top line right here. And then the next time, we're going to be all the way over here at 127, right? And y is going to start going down here like that. So y is going to, we're going to take that base index value, and we're going to subtract yeah, it starts at 127, because this is 127 minus 1, so it starts at 127, so this is the zeroed out value. And we're just going to increment and walk down this edge here. Okay. And once we've done that, the next thing we're going to be on is this bottom edge, and we're going to walk backwards. So we need to take the base index. We need to zero it out again, but this time to zero it out, we have to multiply by the 127 by 2 rather than multiply it by 1. And then once we've zeroed out this value, we need to invert it. So it's going to start at it starts at 0, but we want it to start at 127 and walk backwards. So that's why we're going to do 127 minus. And the IY value is already at the bottom here, so that's why it's 127 there. Finally, here, we're walking up, right? So we're going here, we're going up. So the Y value should be at 0. Or, sorry, the X value should be at 0. And the Y value should be walking backwards, right? So we have to invert... where we had the inversion of the X, now we're doing the inversion of the Y, right? It's the same formula as this, but a multiplication by 3, 127 minus. So that should be the correct formula for kind of walking around here to create a square and doing this in this order here, like that, right? So hopefully we have the right formula for traversal. And we have enough asserts where hopefully if anything is wrong, we'll kind of see that, right? So we can also, right here, we can air check the inputs. Air check input, right? So actually there's only one input, so making this kind of big section for just air checking one of the inputs, probably not the best thing to do here, but we're already doing it. So if dex 2031 is less than or equal to 0, it's greater than or equal to 0, and dex 2031 is less than or equal to dex 2031. Greater than 0, and right, if we're in this range, then we're actually good, right? Okay. Valid range. Else, we're going to say air dex 2031 is out of bounds. Okay. Okay. So yeah, hopefully this will be all the correct math. And now we need to just add everything together, right? So now we just need to add everything together. After we get all these values, it should be pretty simple to... And I'm sure there's like a better, less naive formula for this, like a more mathematically pure formula that involves some type of modulus to get what we're doing, rather than have all these if statements. But we don't really care about performance here as much as just getting the code correct, so we're not going to worry too much about that. So yeah, right here, to add everything together, we have these offsets and we have the origin values, right? So the output value is going to be this cov box value, and it's just cov box4.cov equals the origin ix plus the offset ix. Simple as that. And for the y as well. And we can do some air checking here. So we want to assert that cov box4.cov is going to be less than or equal to 0. Sorry, greater than or equal to 0. And cov box4.cov IY is less than or equal to, this is 256 by 256, so it should be less than or equal to 256 minus 1. Like, if we're going to bounds check this, the most basic bounds, it absolutely has to be, so let's bounds check, right? So, bound check output. So we're going to bound check the output, but there's other checks we can do, right? So we absolutely know that the output point needs to be on one of these, on the border of these rectangles here, right? It can't be a point inside here. It's actually on an exact edge, right? So we could do edge check, right? So edge. So we could edge check the output as well. And that's what we're going to do. We're going to edge check this output. Try to figure out what's going on here. So So the possible values for... So the possible values for the x could be this edge, this edge, this edge, or this edge, right? Those are the only 4 possible values the x can be. The y has the same kind of deal going on. So we're going to duplicate this 4 times. We're going to say if... 1, if none of these cases are satisfied, then we're going to have a problem, right? So IX, this is a 127. This is a 128, right? So this is left edge, inner left. So we have left edge, we have the inner left, we have the inner right. I would rather just call it left edge, then we have the inner left, then the inner right, and then we have 256 minus 1, 255, and that's the right edge, right? And let's just make it int32 bad edge equals 0. And let's just do bad edge plus plus. And let's do the same thing for the y, right? So it should be exactly the same on the y. The only difference is that for the y, what these correspond to are different, right? So this is now the top edge. This is the inner top. This is the inner bottom. And now this is the bottom edge, right? Right, so bad edge. And if it's a bad edge, if the bad edge is greater than or equal to 1, then we're just going to say error bad edge. Error bad output edge location, right? So I think we have enough asserts that we won't have to actually write... I don't want to have to write test code for this, because this is written... This function itself is being written to help test some code, right? So we're hoping we don't have to write any test code for this, because this is like a helper function, to write some geometric patterns here. So we're hoping that this edge check here is enough. This bounds check, this edge check, all those asserts are enough to save our butt, right? So x plus y. Also, we need to make sure that we don't transpose anything, right? So let's highlight all of our x's and all of our y's and make sure that we haven't transposed anything. So the x's, because I just made a transposition error and I just corrected it. So the output x is the origin x plus the offset x. The output y is the origin y plus the offset y. And make sure that everything is correctly clustered, that we don't see any interlacing that looks improper, right? So we should be seeing cyan and orange in this order, right? So it looks like here we got a little carried away. Let's clear all this for a second. So we want cyan and orange, and cyan and orange, cyan and orange. And then for things that are indexes, we'll give them like a purple, right? So a different color that doesn't match up, right? And everything kind of visually checks out pretty well here, right? We don't see any mix matching of those colors from everything we've cut and pasted. So this looks pretty good. This looks like it's going to work. So this covbox thing here is what we're going to return, right? This is the return type, is covbox4. So at the very bottom of the function, we're going to return that return on the stack, right? So we're just going to return covbox4. And there we got it. We got our little helper function. We're hoping that that will be enough. And yeah. So, oh boy, I hope this... this is ridiculous. This is quite ridiculous. Let's put our little breakpoint here. Cool, we got a little helper function. So I know we're using it somewhere, right? So here, in this test function, we want to just say, I want to take this dex 2031, right? And inside of a loop, we want to use it, right? So cov box 4 equals, right? And then call this in a loop, right? So this index max, so the max index, we can just say 4 equals 0. And this is less than or equal to 2031. Dex 2031 plus plus, right? So now we have a loop that can iterate to surround this area, right? So we can form this kind of geometric pattern to test out this function, right? We're going to clear everything, and we're going to try to use this putter function that takes this cov ix, cov iy location, right? So we know that cov ix right, so the IY, so we can check to make sure that's in bounds, even though we already have other asserts in other places, so we shouldn't have to worry too much about it. But just in case, right? So we're going to extract these values and use them here. They're int32 values. The layer index, how are we going to do this? So we're going to like go around here and we kind of want to paint. For the first pattern, I think we just want to paint on every single layer, like go through every single layer, iterate through every single layer, just to see that it's working properly. So what we're going to do here is we're just going to Alright, so let's just do ladex. Alright, and then this offset dex. We're going to take this and do the same thing. And for this, we're going to iterate through all that as well. So we just want a pattern that we can verify, right? So os this is 16 minus 1. We're going to have to adjust this a bit. So move that over like that. Maybe surround this nicely. So that looks a little bit better. And after we go through all the offsets, the 16 bits we want to use, right? I just want to call it cov bits 16. I almost want to call it cov 16. So I don't want to mistake it for index, so I feel like calling it bits B16 for bits 16, right? So B16. Alright, so there's 16 bits here. And for those 16 bits, so it just needs to be half of a pixel, right? So this should be all 16 bits set, right? So all 16 bits set should result in pure white with no alpha. With 100% alpha, right? So pure white with 100% alpha is what we're kind of expecting for this. And then later we'll try like different pure colors, like pure red, pure green, pure blue, etc. But first we want to test the most basic thing and see if we can kind of confirm this in the memory, right? And then after we write this, we want to confirm this pattern in a pragmatic way as well, right? So let's figure out, well, how can we save this to disk, right? So we should have a utility. So we have a thing called picsave, right? So picsave. And does picsave actually save to disk? I believe it does. Yeah, save file, PAINT5D. Okay, so we have kind of like it kind of is hard-coded for these kind of things here. So we actually want this underlying thing here so that we can use, so we can name it something different. So right here we're gonna say we're going to call it P5D 1 OGL test. So 4, 5, 6, and 7, right? So we're just going to give it like a thing to identify it. And we're just going to give it, it's just a test index. So we're trying to test this. So it's test date, it's test, we could say tout for test output. Test output, that, right? So let's say tout 001 test output number 001, right? So tout will be for test output, and that way we can see it, right? So we're editing this when we do it. It's a 512 by 512 bitmap. And we just want to see if this test will result in the pattern we think it's going to result in. Now, the thing is that we have not yet declared all these variables, so that's the thing we got to do. So up here, let's declare all the variables. So declare variables. And then I'm gonna put the music back on. I'm gonna start doing some push-ups because I know I'm feeling kind of tired already. and I want to absolutely get the amount of exercise in that I want to get. So I'm going to try to do more push-ups and whatnot. So I'm actually going to start doing that like right now. Let's look at our screen here. Push-ups. This all needs to be erased. That was... We got our 600 in last week. This needs to all be reset, though. This is 0. This is 0. We actually should try to get 200 in, or 220 in today. Because we might leak into the next day, and we might find that we feel lazy the next day. So, let's try to do out all our exercise for 2 days worth, just because we think we might. I don't want to have to do extra push-ups on other days because I slacked off on Tuesday like last time. So I'd rather just do more. So we're gonna just try to get push-ups in. Here's what we're gonna do. Instead of basing it on the amount of time that we've been streaming for, we're going to get to a good break point, do a few push-ups and things, get to a good break point, do a few things, right? So, so I'll be right back. Yeah. Okay, so usually, every time we do our push-ups and things, we jump on the trampoline. We're gonna save jumping on the trampoline for when we get up to 100. Every 100, we'll do our 100 jumps on the trampoline, because we're gonna waste a lot of time if we walk out to the trampoline for every 20 we do of things. So we're gonna just keep on doing our exercise. Okay, let's get back to this. So let's declare our variables, And let's just start a clipboard stack. CS start, clipboard stack. Okay, so we want to take this and go, hey, this index here, this index here, this index here, this bit value here, this struct here that we use to fetch a rectangle that we're going to draw. Let's just be more uniform and use the shorter hand version of the name. And let's dump this here. So let's do a CS dump, clipboard stack dump. We're going to take all these indices, and it looks to me that this is a bit value. So we want to keep our bit value somewhere else, right? So these are all going to be int32 values. And then this is going to be a uint32 value, even though it's a 16-bit bit mask, just because it's going to be OpenGL compatible, so we only can really use 32 bits. And then right here, we just decided, instead of doing this 0 to 255 thing, we're just going to do it like this. The reason for that is just because we want to have our code a little bit more normalized, and this kind of looks kind of awkward where the cov ix kind of has this. So we could say, we could take this, we could duplicate it, and we could put it right here, right, to note what it was, and then we can kind of like clean up our formatting a little bit, right? And so now everything's a little bit more a little bit more normalized. I think it looks better this way. So yeah, we're going to take this XY value on the canvas user view, and then we're going to take a certain layer that we want to draw on, a certain offset that we want to draw on, and then we're going to put 16 tile values, right? So, so this is going to be 16 tile values. We might also want to make a note of what the heck does this cov b16 mean, right? And so this right here, if we type this, we want to type u plus bonds hexa. Just make a little notification that this is correct. If we type it similarly, we're going to say we're going to correct it. Okay. Now, if we do it backwards, we're going to say it's backwards. We're going to try to save text in memory. But instead of saying backwards U's, we're going to start to abbreviate that as BWU. And then also, if we do something like cov 016 or cov 016, cov 016, wrong, it's a bit field, not an index. Use. So we want to make sure that we have that prefixed b, because it is a bit field, not an index, right? And then if we do something like 016 cov, well, we can't really make that a variable at all. But we're going to still say okay. Now, BWU means if we do a ba, then we're going to say ba hold on. Did I get that wrong? Ba is backwards and wrong, right? BWU oh, backwards dash dash use. That means backwards use. Ba means backwards and wrong, right? And then ba use stands for backwards and wrong use. Right? Use as in a suggestion for what to actually type, right? So that's good there for knowing what that value is there. And then we want to make sure that for we have this thing here. Alright, cov bit 16. Okay, let's do that. Okay, let's put that over on this screen now and kind of keep on going here. Okay, so that looks like a good definition here. And then we're going to save the file. And we're not actually... We still have more testing to do, but I actually want to see if we can output a file that looks correct. So what we're going to do is we're going to get this compiling, and once we have this compiling, we're going to check the file that should be saved in here and see if it's correct. And then we're going to do more push-ups, right? So we want to do a little code, do some push-ups, do a little code, do some push-ups. So int32 is unknown type, so we actually have to... So for this section here, I don't want to have to... So int32... Oh, it's probably not in here, right? It's probably in the other file we're working on, right? So it's probably in the data file. Yeah, the data file. It's P5D 1 OGL structures. So we're going to make a section for the different structures that can exist. And we'll indent appropriately this section. And define int32. Down here, we're going to undef int32. Okay, cool. So now, let's give that a run. So that's at 52. Oh yeah, because we, this kind of thing I like to do, we only need one of them. End of struct. Also, let's say 1, 2, 3, 4. Let's try to, if we really want to do that kind of indentation, let's try to indent all of this to line up with that as well. 1, 2, 3, 4. For func. And then we can do this, right? We can make it look all real nice. Okay. Is that good? Because technically we should... I don't know what we should be doing here. Okay, let's give that a shot. So once we get this running, we're going to visually inspect it to see if it looks correct. By looking at the output, all different tile values, 617 in the underscore file, huh? 617, so right here. Oh yeah, so... Instead of using covbit16, what we're going to call it is B16 like that. Time is 39 minutes. It's going to be up 40 minutes before we get this done. We'll just say 40 minutes. 3 hours, 40 minutes. And we still have to actually write the code for this. So we'll put some breakpoints here. And just say, you know, to do, write the code that goes here, right? So we got to write the code that goes there. Also, this variable here, let's make a note of that, right? So in here, use either So this right here. Okay, also this thing, I don't think we defined this at all either, did we? So we need to define what that is as well. Okay, so that's good. Let's put this over here now. And keep on plugging away here and see if we can get this compiling. Once we have it compiling, we're going to do more push-ups. Unused parameter here, huh? Oh yeah, so this offset dex, we changed our mind and realized that this actually needs to exist as well within our parameters. We kind of made a mistake when we were coding the signature for this function. So lay os and b16. So we're going to duplicate this, and right here is going to be os. And we have actually 5 input parameters, and we thought we only had 4 previously. That also means that we need a no op for here as well to get this running. So let's try to get that running. Covbox 4, unknown type, blah blah blah. So a defined covbox here actually needs to be, and that's in the functions file. So in the functions file where we are defining what covbox is, well, first of all, this is not a uint32, is it? We could call it CB if we wanted to. If we really want to. And do we have a CB anywhere else in this kind of code here? We have a CB that's in a different case. So, right, it's going to be this struct here, right? And wherever we're using this as well, so this covbox 4 here needs to be struct. Right, and we got 1, 2, 3, 4, 5 defines right here. So let's make a note of that. Make sure we have enough defines. 1. Alright, so this is kind of like surrounding this helper function here, and there's 5 of them. So at the beneath this helper function, we also have to undefine 5 of them. Do you want to just mimic the pattern right here? Okay. Let's get that a shot. Once we get it running, we are going to do... Oh! Okay, we are going to do this. So first of all, this thing looks backwards. 126. Is that 126? Yeah, so on 126 here, Looks like we did something really stupid. 126. Cov box, yeah. So we flip that around. It needs to be this way, right? So the type, and then the actual variable name, right? And then the output, right? We're going to set the output, we're going to check it, and then we're good, right? Okay, let's do that. So our formula looks like on 155, it looks like our bracket balancing is completely toasted here. Yeah, so we probably did that everywhere, didn't we? So here, this is probably wrong too. Yeah, it's all wrong. All this crap is wrong. And that probably also means that over here might be wrong as well. Oh, it looks like we did it correctly over here. It's just we did it wrong there. Okay, let's see if we can run this again. Looks like it might. So once we visually inspect what we've done, then I'm going to do my push-ups. Bad output edge location. Okay, so now that we have this failure code, we want to say, okay, well, what is the output edge location, right? Like, so not equal to this, not, oh, so first of all, this check is just wrong, right? So it needs to be equal to this, 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 or this, right? So if it's not equal to this, and it's not equal to this, and it's not equal to this, and it's not equal to this, no, that makes sense. That is correct. So let's printf that, right? Covbox.cov.ix %d \n covbox.cov.ix, right? So we're gonna do both of them. Both these values, we're just going to print them off and see, well, what kind of value did we get? And the next thing we want to do is we also want to know, what would be really important is to know the index that was inputted, right? So the index, so we have, right, we take some input, we try to transform it. So this is the input, and we're checking the output. Let's not worry about the values in between, because we take this value and we want to transform it into these two values here. So %d \n and let's give it some space. So let's do a printf \n just to be able to see what's here. And yeah, let's give that a run. And we can see, hopefully, the output is kind of like obvious as to what the problem is. Covbox undeclared first use in this function. Well, that seems like a complete total. Oh, covbox 4, right? Covbox is only 6, but there's 4 boxes, right? So we're saying that this ix, iy coordinate, is a coordinate on one of these box outlines. There's 4 different box outlines that we could be doing. Okay, so let's give that a run and see what we've got going here. Okay, so the test is going to run. And it's going to fail on here, so our transformation is incorrect. And the index is... oh, that's right. So if x is... Yeah, so both of these have to fail, right? So it could be not on edge. So not on edge Here, let's change this around. So if it's... Let's change this around a bit. We're going to change around this air checking. So if x is equal to one of these, then on left, it's on a vertical edge, right? If it's on one of these, then it's on a vertical edge. And then for this code here, if 0, one of these has to be true. So if 0 or one of these, then this is going to be left, right, top, bot, right? So top, bot equals 1. And this is, you know, on horizontal edge. And the output should be on both edges, on one edge or the other, right? So, so bad edge, sure. int32, left, right, 0. int32, top, bot equals 0. And let's just call this bad EDG for bad edge. Bad edge. On horizontal edge. On vertical edge, right? So is it on a horizontal edge or is it on a vertical edge? Okay. And if top if it's not on any edge, then we have a bad edge. Yeah, if it's not on any edge, then we have a bad edge. There's other ways that we could check, right? Where it could be on... a lot of times it can't be both on the horizontal edge and vertical edge, but the edge case would be like the vertices, and there's a lot of different vertices where it could be. There's like 1, 2, 3, 4. There's 16 different vertices where that case would actually be true, where like there's vertexes, where it shares both horizontal and vertical edge. So I just want a basic smoke test. If it says that it's not on either edge, then it's a bad edge, right? We could do more thorough testing, but I think this is good enough to detect if we're not on a good edge, right? And also, we're going to visually confirm this, so it doesn't really... I think this is good enough. I think this is a good enough smoke test for if things are wrong, right? So let's see what we got. So one of our asserts failed, so let's find this assert. And it's on line 181. So on 181, we have this thing. Oh, well, here we go. 0, 1, 1, 2. 0, 1, 1, 2, 2, 3. And this should be a 3 and a 4. I thought that looked a little bit weird. Right? So we can see visually that the pattern is these 3s match, these 2s match. This is what I'm talking about, writing code in a way where we can visually confirm that the code is wrong by just saying that it looks wrong. 0, 1. 0, 1. 1, 2, 3, 4, right? 0, 1, 2, 3, right? Everything should kind of be continuous. 0, 1, 1, 2, 2, 3, 3, 4. Okay. So let's just, I don't even think we have to check that assert. I think we can just, that was the problem. So let's just run it again and see if we can get this running here. And I know one of the tests is still going to fail, but we want, this is the original unit test that was failing, and that's fine. But what we're hoping now is that in the mod folder, we have this test thing, and if we look at it, I'm hoping to see, so this is all black. Now the reason this one is all black is because we haven't written the code that's going to iterate over this stuff, right? So in the test code, we're iterating over everything. We don't actually set anything yet, right? Because we haven't written the actual functionality here, right? So let's throw an error right here and say error write function body, right? So we're going to write the function body here, but I just want to make sure it crashes here. So we can do like 20 more push-ups. Yeah, write function body. So we're going to do more push-ups and just kind of keep on nickeling and diming ourselves with push-ups. So let's do 20 more of everything and push-ups. So I will be right back. bathroom break as well. So 30. 50. Okay, I thought for a second. This name for this file is really confusing me. So let's give it some more context. Let's open this in Explorer and see, well, what's in this folder? Notes and diagrams, polyfills. Yeah, we included the polyfills in the same place. I don't know if I want to keep it there or not. But I think I should name this something different. Yeah, I think what I'm going to do... First of all, the polyfill file... I think these polyfills would be better off let's take these polyfills and put them into the data file, I think. Oh, no, I can see why they're called POL for polyfill. So it's not exactly all data, right? Yeah, because there's a textile fetch and whatnot. But this name here is just confusing the heck out of me. Let's just rename it to something. Let's get this running, and we're gonna rename that file to like hack or something. Because right now I look at it and I don't know what it is. I think is it data or is it functions? And the reality is it's like a single payload, right? So this right here, let's rename this to something. Let's rename it to so notes and diagrams, polyfills. And this is kind of like the hack code, right? So it's not... really, it's a fragment shader. It's a fragment shader, but it's a fragment shader written in... is a hack piece of code, right? How about rename it to fs underscore for fragment shader? Because let's look at this stuff right now, right? This is written, yeah, this is written to be a fragment shader. It's hack code, but it is written to be a fragment shader, right? So let's just do fs for fragment shader, and then we've broken something by doing that because there's going to be an include for a file that does not exist, and it's in this f file. So let's go in here. And let's look for where this include is. So this is going to be called GLSL shader code using C99. Yeah. Yeah, so let's just call this FS, like that. Just so that when we're looking at this, we can better know what the heck we're looking at, right? So FS for fragment shader code. Cut and paste this into GLSL source code, right? So, so we could literally take all of this, and if we had a build system, we could kind of Hey, so I see somebody stop by. So, because it's kind of like early, I was thinking, you know, I want to be nice to the other C coders that have a schedule. So at 5 a.m., I recommend you tune in to Don Ho, who works on the Keck engine, and he does that in C. Then later at 8 a.m., Hirosa, he works on a UI library that has a way to wire it up to OpenGL, and I think he has other backends besides OpenGL. And then at 1 p.m., you could always turn back into me. But right now, I'm just trying to figure out some test code here. So I have the little schedule right over here on the bottom left of the screen if you want to see who I recommend you tune in to watch. If you are looking for C code, that's what I write. Also, I don't know who this is, because I'm not like a master of Twitch. But you can always take a look at my technical demos. I'm working on a fractal auto-tiling engine that is going to take a lot of proof of concepts from that technical demos page. But anyways, I'm going to get back to it, kind of talking to myself really here. You know, if you like what you hear, you like what you hear. Otherwise, I'm just going to keep with my train of thought here. Oh, hey there. So is that one of the global ones? Yeah. So oh, nice. So I am learning how to. I am learning the way of the. So I see we got hey guys Twitch global. Okay, that's pretty cool. Okay, I like. I will get smarter with how to use Twitch one little thing at a time. So test lost. What we are doing right now. And by all means, tune in to like Don Ho at like 5 a.m. Because I think that my stuff isn't yet at a very interesting point until it starts to get more visual. But hold on. So right now I am trying to get some test code to... hold on. So in my mod folder, I have this file here. Oh, we can't zoom into the file names. That sucks. But I have a file called, hold on, where are you? It's called P5D1OGL Tout, blah, blah, blah. So this is going to be an output file that's going to be rendered when I'm running my test code to verify that it's working correctly. And I want that test file to kind of look like this. But instead of having these different shades with these different alphas, it's all going to be white. And I just want to be able to generate a pattern like this in some of my test code to verify I'm testing the coordinates that I think I'm testing, if that makes sense. So the coordinates you see here that are in color, that aren't black, they actually correspond to this diagram here. It corresponds to going around the edge of this rectangle, going around the edge of this rectangle, going around the edge of this rectangle, and going around this edge, around the edge on this rectangle, right? So this is the canvas user view, and if you set tiles going around the edges of each of these tile patterns, the underlying data structure where the actual tiles are stored, right? So this is where the actual tiles are stored on texture memory. That texture memory, if you traverse just the borders of this in the editor, that texture memory is then going to look like this. And so I want to do that in a unit test, and then instead of just having white, I'm going to set tiles in order to get this section to be red, this section to be green, this section to be blue, and this section to be white or something, just so that I can visually verify that the math is correct, because this stuff is just getting way out of hand, and to have some type of way to visually verify would be good. And then we'll also mathematically verify as well. So we will check that these coordinates are correct in the unit test as well. But before we verify that they're correct in the unit test, we want to verify visually. So we're writing the code that's going to do this. Hold on, I lost my place. I'm going to put that over there. Okay, so in here, we're writing a function. It's called covpix to covbits. There's an I there just because I want everything to be 7 letters. So this stands for canvas user view pixels converted to canvas user view bits. So when I'm talking about canvas user view, I'm talking about this view here. And this view is not necessarily exactly everything that's on screen. It's one step removed from that. So if your viewport was exactly 256 by 256 pixels, if your viewport was exactly 256 by 256 pixels, and your viewport was zoomed all the way out so that the viewport was snapped exactly to this, right? It was zoomed all the way out, basically. If your viewport was zoomed all the way out and your viewport was exactly 256 by 256 pixels, then you could think of this region as screen pixels. Then you could think of it as screen pixels, but it's not exactly screen pixels. But if you had those constraints, then this would be the screen pixels. So you could think of this as screen pixels to screen bits. So if we set something down here, right? If we set some bits here, we want to figure out where those bits are going to be stored in here, right? So screen pixels to screen bits, and then there's a put here, because we have this conversion function both as a putter and a getter. So when it's a putter, we have this parameter here, this last parameter, that gives us a 16-bit value that bitpacks 8 different 2-bit tile values. And if we use it as a getter, right, so the same exact function name. So this is the same exact function name, except it's a getter. It takes all the same parameters except for that last parameter, because the last parameter is an output return value. But you can see the exact same name, the exact same parameters, except this has an extra parameter here. Now, you see the namespace is OpenGL. That's because it needs to work both as OpenGL code and C99 code. So we cannot be doing anything fancy like output parameters that requires pointers, because it needs to run as GLSL code as well. Because if I were to actually write this the way I like to write it, then since this is 5 parameters here in this order, I would like the getter to also be 5 parameters in that same exact order, except the last parameter would be an output parameter, so it would be a pointer to int32 rather than int32, right? And then we could have an exact, it could have more exact symmetry, if that makes sense, because by having an output parameter here on the getter, and by having your return on the getter but no return on the putter, it makes it slightly asymmetrical, and I don't really like that. I like the signatures to be identical for both the getter and the putter. It makes it easier to work with the code, because I don't have to think about what the order of the parameters is. I just know, oh, these two functions, exact same parameter order, but one's a getter, one's a putter. It makes it easier for me to, there's less for me to remember, right? There's less cognitive load, the more uniform I can make all these functions. So anyways, we need to actually write the function body here. But first, we should probably make sure we haven't screwed anything up, make sure this still compiles here, because I don't know. Because I was like all over the place. We just want to make sure it still compiles, and if it still compiles, still fails on the same test it's been failing on, why do you want to also why do you want to be also GLSL? Is it because you want to run it on GPU? Yes, I do want to run it on the GPU. You are correct. So I'm doing something really hacky. So you asked, like, here, let me put this over here for you. So why do I want this to also be GLSL? Is it because I want to run it on the GPU? You are correct. You are correct that I want to run it on the GPU. And you might be wondering, well, like, why am I writing it as C code if I want to also run it on the GPU? So what I've done here is all this code in this file has been written so that it runs as C99. It will compile as proper C99 code, and it'll also compile as GLSL code. The reason I'm doing that is because you can't really test GLSL code, right? You can't really throw exceptions in GLSL code. So we're going to run unit tests on all of this code, and then once the unit tests for all of this code pass, we can take all of this code and directly paste it into a GLSL shader string. So if you look here, we have a define right here. So if defined macro because it's a macro, right? So I want to be very explicit with macros that are defined in different files. I want to make absolutely sure you know this is absolutely a macro. But this is OpenGL. So if it is OpenGL code or GLSL code, then we're going to define like the uniforms for the different blocks of texture memory. And we're going to define the texture coordinate and the fragment color. And if it is OpenGL code, then uint32 is a uint, int32 is an int, ivec2, ivec4, right? tf, texel fetch, right? Etc., etc. All these different assert ends up being nothing, error ends up being nothing, right? Because we can't assert or throw errors in GLSL code. Now, if the code is running as C99 code, then the error is going to be this error function. Assert is just assert, right? And then for texel fetch, we made a polyfill function for texel fetch that will look at the CPU side texture memory rather than the GPU side texture memory, and kind of emulate a texel fetch. And right, so we're kind of trying to make sure that the code runs the same on the GPU as it does on the CPU, right? And that way, after we've written all of these wonderful, wonderful functions, we can test them, we can unit test them, and then we can just cut, paste it into shader code, and we don't have to, like, do little hackish things to make sure it's working, right? Like, when you're trying to write a shader, a lot of times you'll have to, like, make a special, like, air color pixel, and do, like, you'll have to write it in very small incremental steps to work up to the final shader, and it can be a very, very tedious process, and it's not a very, what would you call it? It's a very dirty, not academically pure process when you're writing shader code like that. So we want some type of system in place where we can verify the correctness of our GLSL code by running code on the GLSL code. And the way we're going to do that is by compiling the GLSL as C99 and running tests on it, right? So that is kind of crazy and unorthodox, but I thought it was a pretty decent approach for what I'm doing here. I don't know. I've never done it like this before. Like, usually usually what I do is I will write my shader code as C code. I'm going to read your comment. But I gotta finish my thought. So usually I'd write the C code first, like I'd write a C version of all the functions and test them, and then I would manually rewrite them again as GLSL code. But now I'm trying to do it all in, like, one step, where I can, like, write it as code in a very generic way, where it just compiles as one or the other. So let me put this over here. Okay, so sorry, maybe a stupid question, but is not OpenCL more C compatible than GLSL, so it would be easier to implement your project in OpenCL? You're absolutely correct. You're absolutely correct. 100% correct, without a doubt. The problem is that I did, I made a proof of concept where I got GLSL interop working, and there is a bug in my graphics card that makes it so when I try to do GLSL interop, it doesn't properly share memory. So when memory is trying to be bounced back between OpenCL and OpenGL, every time the memory gets passed between OpenGL and OpenCL on my graphics card, it has to go back down to the CPU, right? So it has to cross the PCI Express from the GPU to the CPU, and then it has to go back from the CPU to the GPU and cross the PCI Express one more time. So it has to take, like, a round trip to go from GLSL code. It has to take a round trip to go from OpenGL to OpenCL or OpenCL to OpenGL. And that shouldn't be how it works, but there's some type of bug in my graphics card. The way it's supposed to work is there is a thing called a quote-unquote zero copy share. There's a thing called zero copy share, and that means that you allocate some memory on the GPU, and both GLSL code, oh sorry, I keep on saying GLSL, but in this case I mean OpenGL code. Both OpenGL code and OpenCL code should both be able to access the same memory location on the GPU when you're trying to do OpenGL, OpenCL interop. That's the way it's supposed to work, but there's a bug in my NVIDIA card that makes it so that I can't do that. And so I was researching, like, you know, the state of OpenCL, and the state of OpenCL really worries me. Like, I got really burned by using Flash and then, like, Flash dying on me. And when I look at the state of OpenCL, I don't have confidence that it is a technology that will be around in, like, 10 years. Like, I hope it's around in 10 years, but my confidence in it is shaky because my confidence was already shaky from what I was reading about it, and like how OpenCL 3 is actually like a reverts to OpenCL 1.0. Like they added too much stuff in like OpenCL 2, and it turned into like a cluster F. It turned into a cluster you know what, and so. And then there's CUDA, right? So CUDA is trying to, what is it? Does NVIDIA do CUDA? I think too. It seems that all want to get rid of OpenCL. Yeah. So I don't want to use CUDA though, right? I don't want to be vendor locked on a certain processor, right? I don't want to have to write code for a specific processor and then have to write it again, right? I don't want to be that vendor locked. And so you're totally correct. In fact, not only like everything I'm doing would be like great, like the algorithms that I'm writing are like perfect. The algorithms I am writing are absolutely perfect for OpenCL. And it really frustrates me that the data structures and the algorithms I have they just fit perfectly with OpenCL. And yeah, it sucks, but the reality is that I need to get something working and I want some longevity in my code. So for now, it's going to be OpenGL. Eventually, once I know some more about Vulkan, I might be able to do some type of CPU, I'll probably be able to do some type of compute shader in Vulkan that does my algorithm more efficiently. But right now, it's just about getting working production code working. And Vulkan is a little bit too advanced for me. So for now, it's just going to be OpenGL code because OpenGL seems like it's here. OpenGL seems like it's going to be here to stay. It looks like Vulkan is so complicated that I don't think it's going to replace OpenGL. I think OpenGL will always be around just because of the complexity of Vulkan. I could be wrong, but yeah, a lot of my technology choices, test lost, are based on longevity, right? It's going to take me forever to make this code work, so if it's going to take me forever, I need technology that's also going to be around forever, right? But yeah, I'm very disappointed in the state of OpenCL, and, you know, it looks so promising, you know, because you had Apple behind it, right? You know, Apple was kind of the reason Flash, well, I'm sure there's other reasons Flash died, but Apple was one of the reasons Flash died, right? Because they stopped supporting Flash. So you're like, well, if Apple's behind OpenCL, that's like a good omen for OpenCL, but then, yeah, it sucks. It sucks, but I don't know, you gotta deal with the reality, so it would be great if I could write these mathematically pure algorithms that don't... Yeah, because, like, right, like, if we look at, so, well, let's look at the data for a second, right? So, if we're rendering if we're trying to render this section on the screen, if we had OpenCL, we could only compute, for this section, we would only need one computation for knowing that all of the pixels in here are within the largest tile size, right? And then for this subsection here, we'd only need one computation to to know that tile size that's 1/4 of the screen is, you know, over these pixels here, right? And then we could keep on subdividing space because we have those like work groups, right? Like OpenCL has work groups, and we could write the algorithm to partition the space properly, right? Like there's a implementation of a Mandelbrot set that uses space partitioning to like speed up the calculations for rendering a Mandelbrot set, and by partitioning the space like that, we could get a lot of efficiency out because we wouldn't have to, like, for every pixel, we wouldn't have to recalculate what space partitions were in if we could use OpenCL. Apple is having Metal now, so they're not interested in OpenCL anymore. Yeah, which sucks because it's like Apple Metal is more like Vulkan, right? Metal is like is your more like gaming graphics, where OpenCL is more for like scientific computation. And I think that's where I'm kind of burning myself, right? Because it's like, you know, maybe I was a little bit crazy to be like, hey, I'm going to try to make a game engine where I use OpenCL for my graphics, right? But yeah, they have Metal. So yeah, you are right. They have Metal. They're not interested. They have Metal. They are not interested in OpenCL anymore, and that sucks. So it's like, great, they have Metal, and now it's like, great. I mean, Vulkan's already complicated enough, but now you gotta learn, like, if you want to know it all, you gotta learn Vulkan and you gotta learn Metal. And so that is part of the reason why I'm not worrying. That's part of the reason why I'm not worrying too much about cross-platform. Like, I want to make sure that whatever platforms I use are stable, right? And OpenCL, even though it's cross-platform, isn't stable, so that's why it's kind of nixed. But I'm not worrying too much about being cross-platform right now, just because of, like, it's such a challenge to get this code working that I don't need the extra cognitive overload of saying, okay, we gotta target this platform and that platform. You know, just get something awesome working on one platform, right? Before you try to get it working on other platforms, right? Like, you know, if you aren't making like a few $1,000s or on your engine or design or whatnot, then why take the effort to like put it into to like make it cross-platform, right? Like, make something awesome that gets attention first, then try to, like, my plan is make an awesome engine, then if it can get some attention, then I would actually like to build like a team and try to get like get somebody who, since I'm working on Windows and I'm doing the Windows side of the code, it would be awesome to eventually get somebody who knows the like Linux side, right? And get it to compile for Linux, because I'm doing like a Windows coding. But right now, you got to get something awesome working first, right? Because if you want an awesome programmer on your team, you got to have a good proof of concept. You can't just say, "Hey, I have this idea." You got to get an awesome program. To get an awesome programmer, or to get anyone who's awesome at what they do, you got to have a good proof of concept. You can't be like, "Hey, I have an idea," right? If you say, "Hey, I have an idea," the only people that you're gonna get is people who aren't that good. That's opinionated and kind of asshole-ish, but that's the reality that I have seen. The only exception might be like if you're kind of like you've already proven yourself previously. Like if you're like if you're John Carmack or Jonathan Blow, I don't think you have to give a prototype to someone before asking them, "Hey, you want to work on my project?" Right? Because you already have a reputation, right? But if you don't have a reputation, you better have something awesome to like back what you're to like get people on board, right? Because nobody wants to put a whole bunch of time into a train wreck, right? We want to put our time into something that's going to be fruitful, right? Okay, so anyways, let's look at this function. So this is the x and y coordinate of the canvas user view coordinate on this diagram over here. Then we have a layer index, which is either painting on the first, second, or third layer, indexed 0, 1, or 2. Then we have the tile set that we're working on, called the OSDEX, or offset index. And there are 16 of them, so 0 to 15 for 16 tile sets. And then we have cov bits, cov B16. It's kind of stutters because cov bits and cov mean the same thing, right? So cov for canvas user view, cov bits. So there's a little bit of stuttering there to normalize this to be the same number of letters as all the other variables. And notice that this is B16 for bits 16, right? There's 16 bits. So this is a 16-bit field, and it's storing 8 different tile values. Each tile value is going to be 2 bits. So we need to put this value somewhere, and this needs to... Now the thing with this is this is going to be kind of weird, because this function, I'm not planning on doing any render to texture. So this function, even though it has an OpenGL namespace, it actually only exists to help test my code. So this function actually shouldn't exist when I'm compiling to OpenGL code. Because like we can do a texel fetch in our shader code, but we can't actually put pixels in our shader code, right? So the way we're gonna do that is we need to wrap this function in a if not defined, right? So if we go all the way up here, right, we have like a if defined, this is OpenGL. We want to take this if def and we want to write something similar, but we need to wrap this whole thing in a... Let's just do... I don't know how we want to format this. We're running out of space, so I feel like if ndef, right? And then do an ndif at the bottom of this. And just say endif. And then we can make a comment. Right, that kind of, I'm gonna kind of break my formatting a little bit, but it's kind of one of those things where I kind of need to notice it, where it's like, one of these things is not like the other, one of these things is not like the other, right? So this thing right here, we need to know that this, even though it's in this file, and it is going to be pasted into the GLSL shader code, but it's never going to exist in the GLSL shader. It's going to exist in the GLSL shader string, but it's not going to compile. So if not defined, this is OpenGL. So it only exists. So let's make a note of this. So at vid IID. So 0105, and the time is, by the way, it is 7:18. So, like, by all means, check out like Don Ho and Hirosa right now, because I mean, I don't want to really step on their toes. So that's why I put in the bottom left a little schedule. So, anyways, I just couldn't sleep, so I started coding at like midnight, or actually like 2 a.m. or something, because technically it was Monday, so I'm like, okay, I can't get to sleep, just drink my coffee now and just get to work. Anyway, so the time here is 4 hours, 41 minutes, and let's just call this 40 seconds, and say, this code only exists to test the getter function. So it only exists to test the getter function. Get. We cannot put pixels within GLSL shader code. Hence, the guard used to Okay. So yeah, this thing right here, just a little note of like why the heck is it the way that it is, right? So we just want to absolutely know, like, there is a reason why we do not want to compile this. And the video is 1:05, and we're at 4 hours, 41. Well, this is past... so let's do this. 4 hours, 43 minutes. So the reason why this is guarded like this, if not defined, this is OpenGL, is because this is a put function and we cannot put pixels inside of GLSL code, right? That's not a thing you can do in GLSL code. And hence why this has a guard around it so it won't compile in the GLSL fragment shader code. So, done explaining. Okay. And maybe we'll say explained instead, right? Okay, so let's figure out how to write this. So the first thing is let's just nuke all of this, right? Because we don't need those. We do not need those no ops anymore because we're actually going to calculate things. And I know that we have some. If we may have some conversion functions that already exist to kind of help us. So let's see what we have. So, not what I thought. I thought that we actually had some type of conversion function already. Oh, no, we have the opposite conversion function that goes from paint pixels, but we don't have this function. Okay, that's fine. I just thought we had this. So let's think about how we're going to go from a point on this diagram here to a point on here. And there's multiple points on here, right? Because depending on what tile size we're putting, it's in totally different locations. So let's figure out for any canvas user view coordinate on here, it's going to resolve to either a coordinate somewhere in here. It's going to resolve to coordinates in here, coordinates in here, coordinates in here, or coordinates in here in the texture memory. But no pixel in the canvas user view here is going to straddle a coordinate somewhere in one of these blocks and one of these blocks simultaneously, right? All the data is going to be isolated to either here, or here, or here, or here, right? It's not going to straddle anything. So the first thing we can do is figure out, well, which one of these segments are we in, right? So let's do like int32 and say like we could do, I feel like being a little verbose, more verbose than I usually am. So let's do this. Tile layer OX for tile layer offset X and tile layer offset Y, or origin X, origin Y, however you want to think of that. And to figure out what this is going to be, let's say that equals, and so for this we have a shorthand, right? We have this shorthand, and let's just paste this right here, and then think about what it actually is, right? So, the range for the IX, IY value, so that IX, IY value is actually this canvas user view value, and I don't actually know if I like using the macro here. I almost want to use... I feel like I'm going to get confused, but... well, actually, let's not get too picky yet. But, right, so... Right, we just want to shorten the variable names a little bit when we're calculating this. And any coordinate inside of this block needs to have an origin of 0, 0, right? Because it's this memory block here. Any coordinate inside of this block needs the origin to be right here. Any coordinate inside of this block needs to map to an origin right here. And then any coordinate inside of this block on the canvas user view needs to end up being origined here, right? And so we know that the coordinate is, we have these 128 by 1, this is 128 by 128, right? So all we need to do is say that divided by 128 and divided by 128, because the division is going to truncate because it's C code, and GLSL code also truncates the same way as C99 code, except remember this is only going to compile as C99 code, so we don't have to worry about the GLSL aspects. But this should be correct for, well, hold on. Yeah, this is either going to be 0 or 1. This is going to be 0 or 1, right? So we could also assert that this value here is greater than or equal to 0, and it is less than or equal to 1, right? The range of these two values is between 0 and 1, right? So let's assert that that assumption is correct so that we can keep on coding a little bit further. So once we know the origin, we have to iterate through the different memory blocks, and first of all, we need to figure out how are we going to do this. So this variable, the offset dex, that's just going to tell us which bits of the pixel we're looking at, right? So we're not that far, right? We still have to figure out what pixels we're looking at before we worry about what bits of the pixel. But the layer index right here, the layer index, well, that means like if we're setting the biggest tile value, are we doing this layer? Are we doing this layer? Or are we doing this layer? So the layer index is actually going to change the offset, right? But the tile size also changes the offset, but we want to set values for every single tile size. So we need to iterate through every single tile size and extract the 2 bits from this value and then set them onto the CPU side canvas. So we know we need a loop for the bit index. So let's say that like for, how about, do we want to say bit index, or do we want to say, I think, so this offset dex is, oh, you know what, so we want to loop through the bit index. Let's not call it bit index, let's call it tile exponent. So we have, so things make a little bit more sense, because we want to go through every single tile exponent, and the tile exponent is going to be less than or equal to 8 minus 1, and the tile exponent plus plus, right? So, so here we're going to loop set all 8 tiles under cov. So we want to set all 8 tiles under the canvas user view pixel coordinate, right? So that's what we're doing in this loop. So we just want to mark that as such. Okay. And, you know, we could make a note that TE equals tile exponent, and we could also do something like this. We don't have to use it, but if we want to say, like, til exp is TE, right? So if we want something where we can just document that. So TE is my shorthand variable name, and then tilexp is my long-handed variable name. They both mean tile exponent. Tile exponent is the tile size, right? So the tile size can be 0, 1, 2, 3, 4, 5, 6, or 7. And that stands for 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, etc. Because each tile is... each tile size up is twice the size of the previous tile, right? So if we're going to use this, we need a variable declaration section. So where are we going to put that? I think that it'd be a little bit easy if we could just make a declare variables right here. Make a variable declaration section right over here. And so we're kind of going to do it in a... I don't always do it in a C89 kind of way, but sometimes it is kind of nice to have like a front-loaded place where you put all your variable declarations, I think. Origin of tile layer data. Yeah, so one is the X, one's the Y. And then we also want the tile exponent, right? So, so for this, the tile exponent, and also you might notice that this code is a little bit different than other code I was writing, where I had very precise bit widths, and now everything's like a signed or unsigned integer. The reason for that is any code in this file is going to be written in a way where it, even though this isn't going to be compiled as OpenGL code, like all the code in this file does not have the luxury of like 8 bits or 16-bit bit widths. Everything needs to be 32 bits, signed or unsigned, because it needs to... Right, if stuff is compiled as shader code, we don't have the luxury of specifying those different bit widths, right? And so we're getting a little bit sloppier with our bit widths than we should be. How you handle when exp is higher than, for example, unsigned int. Hold on. So let me put that down here. Okay. How do you handle when exp is higher than for... let me move this over here. Is always the range so I don't know if I answered that quite correctly. So you're talking about like if it's higher than, how do you handle when x is higher than, oh, so you're talking about like, are you talking about like if I, you know, it's an int32, so it has a range that is, I'm not sure if I answered your question or not. If I didn't answer your question, feel free to kind of rephrase it. But I'm going to explain with the diagram a little bit to explain the range of that value. So this is a 512 by 512 block. I get it is, so the depth of tiles is from 0 to 7. So it's the tile size that is 0 to 7. So this is, and I actually have a visual demo that I'm going to show you really quick. But this is 128 by 128 very small tiles, right? So right here in the canvas user view, there can be 128 by 128 very small tiles, okay? And I know I've explained this before, but okay, so right here, this is 64 by 64 bigger tiles, which also exactly covers this area. Then right here, this is 32 by 32 even bigger tiles that exactly covers this area. And then once you get down to like all the way down here, you have 1 pixel that encodes 1 very large tile that fits over this entire area. And I actually have a technical demo that you may have not seen because it's not on my demos page. So I'm going to show you that really quick. So I think it's called For Andrew 01 maybe. I was going to show my friend Andrew this, so hence why the shortcut is named For Andrew. And this is a very cluttered demo, so it's kind of hard to see what's going on here. But you can see that there's these... I'm going to erase the tiles. So you can see there's these small tiles, right? So these small tiles that I'm erasing right now, see these small tiles I'm erasing? Those small tiles would be stored in memory here, here, or here. It's a slightly different data layout. But basically it would be, right, because this layout is slightly different than the memory layout here, but it's the same basic concept of you have 3 layers of very small tiles, then you got 3 layers of even bigger tiles, and then 3 more layers of even bigger tiles, etc., etc. So the tiles that I am erasing right now, this is exp equals 0. So right now I'm erasing exp equals 0. Tile exponent equals 0. That is the tile size that I am erasing right now. Okay, so let's go up 1 more tile size. So you can see this tile size 0. I'm going to go up to tile size 1. Okay, so now the tile size I'm erasing, it's a little bit hard to see, but the tile size I'm erasing is exp equals 1, right? So 2 to the power of 1. So the relative size is a 2 by 2. So the relative size is relative to the smallest tile size. So the tile size, because they're relative tile sizes, what is the unit? What is the relative tile size unit? Well, the relative tile size unit is called a pebble, right? So when I say the tile size is 0 here, I mean the unit I'm going to use for that is called a pebble. So this right here, this thing I'm erasing right now, is 1 by 1 pebbles, right? So when you're looking at this canvas user view, right, and it says 256, it's 200. This is 256 by 256 pebbles. Now, I know that a lot of times you can think of this as 256 by 256 pixels, but it can be a lot easier to think of it as pixels. And that does work if the camera is exactly zoomed onto this and your viewport is exactly 256 by 256, then 1 pebble will equal 1 pixel, and then you can wrap your head around it and think of this as pixels that map to this data structure here. So let's just go through this again and say, okay, so what about tile size 2? Let's go to tile size 2 and erase some of those tiles. And so you can see it gets a little bit harder to see these tiles because there's so much data here. And I really wish that I would have made a clear screen button for this, because it gets so cluttered where you can barely see this gigantic tile. You can just see this little strip here. But we can't isolate all the tiles of a certain tile size. So this says show same tile sizes. So if I click this button, then we can see all of the tiles of a certain size. But I'm doing some parallaxing where the different layers are further back, right? So we have 1, 2, 3 layers. And this isn't the way I'm going to render the tile set data. This renderer right here is kind of rendering the level map data, and so I render it slightly different, but it's the same basic concept of kind of like using this kind of like MIP map, this MIP map like structure to densely pack a quad tree, right? So we're trying to pack a quad tree-like structure or a mip-map-like structure into a whole bunch of pixels and then be able to render it, right? So we could go to the bigger tile size, so we could go to tile exponent size equals 3, and then we get even bigger stuff, right? And then we could go to 4, right? We can go to 4, right? And we can keep on getting bigger and bigger and bigger, right? Now, so this is the basic concept of how we're going to render kind of a nested tile design, right? So this isn't the fractal aspect of the engine, but there's a lot of different aspects to this engine, right? We have layers, and we have tile size nesting, right? So we have layers and we have tile size nesting, where we have this quad tree structure, but the quad tree structure where we're nesting different tile sizes is not the fractal aspect. That's a totally different aspect. So there's like three, like, I don't know, you could say 3 big brain quote unquote concepts that are going into this engine for creating this tech. And so this is one of those big brain concepts. Like if I made a list, let me think of a list right now. So if I were to make a list of the main engine features, one is we have auto tiling of tiles. Subtiles of tiles are drawn using other tiles instead of pixels, creating fractal auto tiles, right? So we have basic auto tiling. We're going to have basic auto tiling, okay? So auto tiling of tiles, right? That's a basic kind of thing that everyone knows about, auto tiling. But then tiles are going to be drawn using other tiles. So instead of drawing a tile with pixels, we're going to draw the tile with more auto tiles, right? So take the pixels that usually makes up a graphic that is in a subtile of an auto tile set, and instead of drawing that graphic with pixels, we're actually going to draw that graphic with auto tiles. And that's going to give us the fractal auto tiling aspect, which we don't have a technical demo for, because it's a little bit complicated, so it made more sense to just implement it in the final engine design. So we don't have any example of this yet, and this is not what we're working towards for this first editor. The first editor is just going to be, well, let's kind of like, so the first editor is just going to have tiles. Each auto tile design has can be drawn with different. Each tile design contains different layers and tile sizes, right? So you can draw something, as you're drawing your auto tile design, you can draw it with small tiles for detailed features, and you can draw it with larger tiles for more coarse level features, right? So each auto tile design contains like different layers and tile sizes. So that's what this kind of stuff is going to be about, right? It's going to be about when you're drawing it, you're going to have, conceptually, it's kind of like having different pixel sizes for your artwork, right? Okay, so one aspect is these different layers and these different tile sizes. And another aspect is each offset auto tile set has only 4 graphics and the 16 subtiles needed for proper weighing auto tiles is generated from those 4 graphics. So this is another aspect of the engine. So might want to like put this in the README. So I'm going to renumber these, by the way. So this thing here, if we're looking at right, the editor, the first editor, the PAINT5D editor, is going to be used to create the 4 graphics, right? These are going to be the 4 base tiles to create the auto tile set. So right here you have the top left corner, the top right corner, the bottom left corner, the bottom right corner. And to create a edge tile on the left, you're going to take some of the information from this tile and some of the information from this tile and procedurally generate a left edge tile. And for the right edge tile, you take some of that top right tile and some of the bottom right tile and procedurally generate a right edge tile. Over here, we generate a top edge tile, generate a bottom tile, and then, you know, we similarly slice and dice everything to generate all of the 16 tiles we need for a proper auto tile set. So the touching all tile would be kind of like taking a little bit from all of them like this, right? So let's actually kind of keep on doing this. So auto tiling of tiles. So auto tiling of tiles within a rendered level map. And tiles are drawn using other tiles. All right. So these are the main engine features I'm going for. So let's actually take this like kind of list, because I think that's a good thing to have here. Let's go into our README. The README is kind of out of control here, but let's go into the README here. And we have a summary. We have, like, these goals are... let's just call this engine features. Engine features. Alright, we'll just make a little section called engine features. And we'll figure out where to put this later. Engine features. Okay. So these engine features. Right, so the engine features that we want. Now, different systems, not all systems are going to do all of this, right? So, so layers and tile sizes, PAINT5D, PAINT5D is the system for creating these graphics. Now this is a different system that does not exist yet. We're just working on PAINT5D right now. This part is not going to be part of that. Auto tiling of tiles within a rendered level map. Different subsystem. Tiles are drawn using other tiles instead of pixels. So this is the only thing that PAINT5D covers. Each auto tile design contains different layers and tile sizes, right? So that's the PAINT5D subsystem does this part, right? So PAINT5D subsystem does this part. I don't know what these subsystem names are yet. So this is a future subsystem does not exist yet, right? So this subsystem does not exist yet. The subsystem that does this does not exist yet, and the subsystem that does this does not exist yet, right? So what we're doing is, since we want to make the graphics fractal, before we make things fractal, I thought it would be a good idea to have what is called a terminal tile, right? Like, the easiest way to get this render up and running is to have these tile designs where eventually we want to render things as fractal, but we want some type of base pattern. So as we're like zooming in to the... Once this engine is up and running, we want to be able to zoom into and zoom into and zoom into the tiles to see all this fractal goodness. But eventually you want like a terminal level where you cannot zoom any further, right? And that's going to be the patterns that are created in PAINT5D. Now, eventually, we could change the rendering engine where once you get to a terminal tile, it becomes self-referencing, right? So the tile values that are specified in PAINT5D, instead of them being drawn with pixels, they could be drawn with tiles defined in PAINT5D. They could like self-reference each other so that we could actually get an infinite zoom even though we have finite data, right? But before we try an infinite fractal zoom, I just want to get like a fractal zoom where we're not doing any type of like infinite looping references. If that makes sense. So PAINT5D is going to be these terminal tile values. We want to layer on the tech kind of one piece at a time. We want to build up, right? We do not want to try, this is very ambitious, right? So we don't want all of this ambitious stuff all at once. We really want to focus on one thing. So this one thing that we're focusing on, if you want to see that in kind of action, the one thing that we're kind of focusing on, if we go into our demos, and you want to see, well, what are we focusing on right now? So what we're focusing on right now in terms of tech is like this guy right here. Something like this. Not exactly this, because this tech has 4x4 base tiles, or 4x4 subtiles, right? The tech we're designing needs to only have 4 tiles, right? So this is an auto tile set designer that I made in Golang, and I have a little terminal I made with it. Let's see if we can just go to YouTube and full screen this baby. So what we're trying to work towards right now is a auto tiling renderer that's going to allow us to design tiles that have this quad tree kind of structure where we can have different quote-unquote pixel sizes, right? So you can see how I'm drawing with these different pixel sizes, and we want my artist Josh to be able to edit these base graphics so that we can use these base graphics as auto tile sets in the rendering engine. But it's not going to be exactly like this, because you see that there's 4x4. There's 16 of them, right? Because Wang auto tiles have 16 subtiles per auto tile set. Now, our engine is going to internally use 16 tiles per auto tile set. However, we're going to only require the artist to create 4 graphics, and the remaining 12 graphics are going to be auto-generated by the engine. So let's pause this right here, right? So we got 16 graphics, but in my little diagram right here, we're only going to have the artist generate 4 of these, right? So they're going to draw the top left, the top right, the bottom left, and the bottom right graphics. And then from there, right, we're going to procedurally generate everything else, which I've kind of already described, right? So this is what we're working towards right now. So we have all this stuff we want to work towards, but the first part is just an auto-tiling engine that enables you to make these like awesome auto-tile graphics with 4 times faster than any other engine, right? Because every other engine that uses auto tiles requires you to draw at least 16 graphics, but our engine is going to require you only to draw 4 graphics to create an auto tile set. And not only are you only going to draw 4 graphics, but the visual style of it is going to be very distinct, very unique, you could say, right? Because we have this is going to result in a visual style that is not going to look like any other engine. Anyways, so I don't know, Teslost, if I kind of answered that question or not. Now, as you phrase it, the depth of tiles is from 0 to 7. You are correct about that, because the larger tiles are going to be rendered like behind the smaller tiles, right? So the tile size is kind of like a depth. And then, but we also have layers as well. So we have layers 0, 1, and 2. So all of the tiles, so the way we're going to render everything is, I think the first renderer is going to take all of the tile sizes in the backmost layer and alpha blend them together. Then take all of the tile sizes in the midground layer, alpha blend them together, and then take all of the tile sizes in the frontmost layer and alpha blend them together. And once we have these 3 composite images, then it's going to take those and do like an opaque blend of those 3 composited those 3 composited layers. So we're going to composite like this, and this data, right? For the first layer. Then we're going to composite this data, and this data for the second layer. Composite this data, and this data for the third layer. And then once we've made those 3 composites, then we're going to do an opaque blend of those in a back to front kind of order. So I hope that kind of answered what's going on. I know a lot of this is just gonna like not make sense until like I have it down, until I like have it actually rendering something. So don't feel bad if you don't understand it, because like it's a whole bunch of crazy ideas, and there's no. It's not like me writing a normal rendering engine where there's already these like very well established mental models that you could have studied ahead of time, right? So like a lot of these mental models are kind of new, right? They're kind of new, or at least as far as I'm concerned, they seem like mental models that are not existing in any other engine, right? So you don't have a so it's totally okay if you don't get what's going on, because like this is an engine idea I've had for 8 years, and I finally figured out all the tech. I finally did all the proofs of concepts and figured out what language I wanted to use. So like, don't feel bad at all if like maybe that explanation does not make perfect sense, because it's like this is I would like to think that I'm on the cutting edge of something, I would like to think that, maybe I'm not, maybe I'm completely full of myself, maybe I'm full of crap, but I think I'm onto something here, right? So don't feel bad if you don't get what's going on completely, just as long as you have like a high level understanding of what's going on. As long as you kind of like so as long as you have like a little bit better of an understanding, and it's going to get your understanding of this is going to get better as I actually get like a rendering engine going, right? Like before there's an actual rendering engine, once there's like rendering code, then we can say, here's what it looks like when it's rendered. Here's the underlying data structure, right? And then it'll make more sense, right? Because then I'll have something to kind of point to, right? Right now, you just kind of have these like, oh, here's a random technical demo done in JavaScript, and here's this ASCII diagram, and that's pretty good, but it's lacking. It's lacking. It's like the vision is kind of like it's only in my head, and that's kind of like I'm thinking that if I don't code this, I think that. And like I said, maybe I'm being egotistical here, but I think that if I do not code this, I think it's going to be at least 100 years before this gets coded, if that makes sense. I think that my specific insights and my specific experiences as a developer, like my obsession with fractals and my obsession with auto tiles and my obsession with making a like bomb game where we can explode the geometry and have that geometry relatch together. Those three obsessions that have given me the insight to create this engine, I don't think I I don't think anyone else has that specific obsession, right? So it's not that there's not somebody out there that's smart enough to do this. I think there's plenty of people out there smart enough to do what I'm trying to do. However, I'm the only one who is both smart enough and interested enough to do what I'm doing, if that makes sense, right? So I'm like, I gotta get this done, because if I don't do this, no one else is going to get it done, and this is never going to be seen. And I want this tech to see the light of day. So I'm going to keep on doing it until it gets seen, and, you know, hopefully I don't, like, die or something before that happens. Hopefully I can kind of explain it well enough that maybe eventually I'll get somebody else on the team who kind of, like, shares my vision. I really do want to find someone else who kind of shares this vision and who is kind of enthusiastic enough, because, you know, yeah, I just hope I live long enough. I am worried about that, though. It was just kind of morbid, but yeah, yeah. Supposedly, the chronic illness I have doesn't actually shorten my lifespan by too much, but I am... That's morbid, but yeah, I am really worried. I really want this to... you know, dying terrifies me. Not doing anything meaningful before I die is also kind of worrisome. Not as worrisome as dying. Like, that's the most terrifying thing, but the second most terrifying thing is not having accomplished what I want to accomplish before I die. So this is literally... what I'm working on is literally what I want to accomplish before I die. So you feel the same? Yeah. Like, man, like, yeah, like, yeah, so that's good. While we're here, while we're kind of, like, ranting, what kind of, so what kind of, while we're here, you know, I might as well ask, like, do you have any projects you have, like, ideas for? I know I'm kind of ranting anyway, so I might as well kind of ask. I don't mean to put you on the spot, though. Like, I know that sometimes, you know, sometimes we don't have things to work on, but we kind of, like, right? We all, I think that most of us have a drive to do something meaningful, right? And sometimes we don't know what that meaningful thing is yet, right? But we want to find it. You know, sometimes it comes down to, like, sometimes you're in a position to create, and other times you're more in a position to absorb, if that makes sense. Like, creativity does not happen in a vacuum, right? So, like, you have to get some data in your brain before you can output something, right? Because the brain kind of transforms data. But yeah. But anyways, if you have anything, just throw it in there. Also, I do understand, like, if you don't want to say, because I know, like, it is kind of risky kind of putting out your ideas there, right? We don't want our ideas stolen or whatever. But I've thought about it, and I realized that what I'm doing is so complicated that no one else is really going to try it. I think somebody else might try what I'm doing, but they're not going to try it until I've already done it, right? Like it's such a complicated idea that takes a lot of work, and it's one of those things where I don't think anyone else realizes how worth it is to do this until the tech already exists, if that makes sense, right? And like I'm taking, right, putting your ideas out there is risky. It's kind of scary. Like, I am kind of worried, like, okay, I'm just going to put my source code out there and let other people look at it. But I'm like, you know what? I'm going to do it just because I think, you know, yeah, it would suck for me not to, like, profit from what I'm doing, But what's even worse than not profiting from this is the tech not even existing at all, right? So I want this tech to exist, and to make absolutely sure this tech exists, I think the best course of action is to kind of like make it public what I'm doing. And I am putting a license on the engine, right? Like if you use the engine, as long as you make under 100,000, you don't owe me anything, and then everything after $100,000, some type of royalty. I'm basing the royalty amount based on the price, a fraction of the price of a cup of coffee, or something like that. I forgot exactly what I put in the license. I'm working on projects for material science computation. It is for the libraries of the computational materials. Currently, I'm doing Python lib for Open CalPad lib. Hold on, let me Open CalPad lib. So I don't actually know. Open CalPad lib. Is that how it's spelled? Let me just take a look there for a second. Open CalPad. So I once met a material scientist, and holy crap, they are smart. Like, so, you know, I had this experience where, like, when I brought my girlfriend or the girlfriend at a time to a programmer party, they always complained that they had no one to talk to and they couldn't understand anything that was being said. I went to a party with a whole bunch of chemists and material scientists, and boy, I couldn't understand what the hell they were saying either. So, like, but I mean, I guess that's what happens when you have a very specific discipline, right? You start talking in a language that's pretty much foreign to anybody who's outside of it. Open CalPad is an informational international collaboration of scientists and researchers interested in the development of free, high-quality software and databases for thermodynamic calculations for all kinds of applications. Okay? So, I see that. I see thermodynamics, and I'm like, okay, so that makes you pretty damn smart. That's what that says. Yeah, it's a language barrier, right? Because you need a lot of like you need for people to communicate, they need common experience, right? When I say something's hot, the only way somebody can know what the hell I'm talking about is they have to have experienced what hot is, right? If I say something's cold, same thing, right? And when we get into more complicated disciplines, it's the same thing. They have to have experienced those mental models. And that's kind of like why I understand, it's a language barrier. And when you're creating a new rendering engine, which I am, it's like there's also this language barrier where I have to come up with these concepts and make up my own words for things, right? So covpix, right, for canvas user view pixels, right? I have to come up with a term for that. There may be another term that already exists, but I'm just going to come up, if I don't know a term for something, I'm going to come up with my own term, right? But yeah, you have a language barrier, right? You're totally right about that. So anyways, so I kind of ranted here. Let's try to get this working. But yeah, material science, yeah, like the material science people I know, super smart people. Like, even their answer for, like, you know, I asked, like, you know, if aluminum is thermally conductive, why is it not electrically conductive? And the answer is, well, it is, but it immediately oxidizes when it's exposed to air. And they gave me that answer, but even when they gave me that answer, it was like right at the edge of my understanding in terms of, like, how they phrased that. But I don't know how I don't know much about material science, but it's kind of my assumption that if something conducts heat, then it should also conduct electricity. But I don't know if that's always true. But I've kind of always assumed that there's no material that conducts, and I don't know if you know the answer to this, but I'm pretty sure that if a material conducts heat, then it also conducts electricity. If it conducts electricity, it conducts heat, right? Now, I could be wrong about that, but it's just my experience and my intuition. But you might have a better intuition about if there's like some type of material that breaks that rule. Yeah, aluminum builds an oxygen layer, yeah. But yeah, so you could say, like, technically aluminum is conductive, but it just has that layer around it that keeps it from conducting, right? Anyways, so where are we? So let's try to write this. So the tile exponent, TE for tile exponent, right? So let's do til exp, tile size exponent. And we're going to loop through every single tile exponent. And for every single tile exponent, we want to get the location of the data, right? So we're going to need an offset for... Well, we have this layer right now. And... Hold on here. This is not the correct variable name here. These things here, these origins here are not layers. These origins are not layers. These are the different quadrants. And I made a mistake here. This is quadrant. This is the quadrant. Which sub-tile graphic are you drawing on? There are 4 of them. This is the origin. So really this is the, yeah, I got that wrong. This is the quadrant. It's the quadrant offset. And, right, because we're dividing by 128, right? So this 128 here, we're trying to figure out which one of these quadrants are in. So I made a mistake there. So let's do, this is going to be qua for quadrant. And then we can take this and we can paste over here. I made a mistake as I was doing this. So that's the quadrant. And then, as we're going through each one of these, we have a layer, right? So, this layer index, we do need to figure out a layer offset, right? And the layer offset is going to change depending on what the tile exponent is. So, and it's actually going to be... what are we going to call this? So it's going to be tile layer. The offset could also be considered an origin, right? So where the first pixel is for a certain thing here. And we should have a tile exponent to... I don't know if we actually have a formula for that, but maybe we do. So let's look at that. So, so we might have a conversion formula that already does this. So tile exponent to maximum coordinate... so we might not have one. Tile exponent to diag pix. Yeah, we kind of have some stuff, but not exactly what we need. So, we really want some type of formula where we take the, we want to take the layer that we're on, we want to take the layer as well as the layer as well as the exponent size to get an origin, right? So these different origins for these different blocks, we need a layer. We need to know what layer it is, and we need to know what exponent size it is, right? So, and then we can find an origin, right? So, what are we going to call this? How about tile org equals, let's make a function, I don't know what to call it, some namespace. We actually call it like OpenGL. And it's going to be, we need the exponent as well as the layer. And it looks like when we look at the order of variables, it looks like we do the layer and then the exponent size. Is that the order we really want to do it in? Oh wait, no, this is not the same thing. Layer dex. There's no exponent size here. I want to make sure that I have things. I'm very picky about the order of parameters. I want things to be very consistent. So I want to look at my PAINT5D notes file and look at some of the signatures in there. And it looks like we have quadrant, exponent, and layer. Okay, so now that I know that, it's going to be exponent and layer, right? So right here in the parameters here, we have layer, but we don't have the exponent, right? Because the exponent is embedded into the bits here for this function here. But when I look at the signature of this function here, it looks like we go exponent and then layer. So since we're going exponent then layer, I want to keep that kind of consistent ordering. So over here, we're going to say some type of function where we're going to take the tile exponent and then the layer. And so it's going to be tile exponent and lay dex converted into and I guess it's going to be what are we going to call these origins here? I guess it's the origin. So we have local IX, local IY. I guess technically it would be org. I guess it's the origin. Tile origin. Tile origin, I guess. I guess that's what we could call it. Let's look at I want to look at my notes really quick in terms of like what I am using in here. I know I have like, so if I go look for like Control F and I look for till org, I probably don't have anything, do I? No, I don't have anything for tile origin. I guess we could use tile origin to mean kind of like, this is the tile origin for this data set, this is the tile origin. But is it tile origin or is it like a local tile origin? So let me think about like, what do we want to call this name here? So we have like local IX and local IY. So for like any one of these blocks, there's local coordinates in here, right? So for this block, it has a range of local coordinates. And for the origin, so it's kind of like the origin of the local data. So maybe we want to call it like I know we had like tile origin IX, so maybe we want to call it like instead of till org, we want to call it like local origin or local tile origin. I don't know what I want to call it. I know this is like taking a lot of time, but I want to have names that once I pick a name, I want to always use that name, and that name always means the same thing throughout the code base, right? So when I see Tillay here, right, if I search for Tillay in the code base, I should be able to like find everywhere that's always used, right? So the same thing for this tile origin, right? So I think tile origin kind of makes sense, but the tile origin could mean a lot of different things in a lot of different cases. So I really want the I really want to know tile origin. Well, let's kind of think of what we could call it. We could call it tile origin dot, local IX. We could call it maybe tile origin is the right thing. I don't know. Or maybe it's a segment, right? So it's paint. So, I don't know, we could call it P5D segment origin, right? Or, well, we already have Tor IX, so what about, PAINT5D, tile origin? I don't know, man. But I'm just worried that I want to pick something that makes sense when I look at it, but I don't want it to be kind of too generic. So PAINT5D tile origin, and then we could return a struct, and then we could do dot. I know we already use like local IX, local IY everywhere, so maybe we could do like PAINT5D tile origin like this, right? I think I'm going to go with something like that. And then in our shortcuts here, we're going to make a note of this, what we've been thinking about, right? And I know that it's like, man, you're taking a long time to like just come up with a variable name, but a problem well defined is a problem half solved. So pick backwards, try P5D Tor. So let's just make a note of what we've been thinking about. So if we type this, PAINT5D Tor for tile origin, we'll write a little check mark to say, hey, you got it right. Good job. Excellent. If we do something similar enough, P5D Tor like that, then we'll kind of just correct it, right? And type it correctly. Now if we do it backwards, so if we do Tor P5D, or Tor P5D, or Tor underscore P5D, we're just say backwards And we have more spam in the chat. Oh well. Backwards, use P5D Tor, right? Okay. And then we want a definition for this as well, right? So what does this mean? And if we type this, PAINT5D tile origin. Origin of P5D data segment of pixels. Something like that, right? Okay. So now that we've kind of like figured that out, let's go look at this and say, well, for this function, instead of calling it tile origin, and also, hold on. Okay, good. So we have this thing, we're going to take the tile exponent and the layer index, and we want to convert it to this, we want to convert it to tile origin, but it's going to be called P5D Tor, right? P5D Tor. And when we do this, we need a corresponding piece of data here. So where the heck are we going to put this, right? We said this is the fragment shader, and all of a sudden we're like, hey, let's make this kind of like helper function thing. Let's just throw... I like to usually subdivide my... We're just going to throw it near where it needs to be used. And it's kind of ugly this way. But let's just throw it in here for now. Until time decides that we... Until something decides that we need it somewhere else, right? So let's just throw it in here for now. And let's just call it AAC 2020 P5D 1OGL. Right, so project namespace, subsystem namespace, and then right here we're going to call it P5D Tor, right? So P5D Tor. And that'll be the type. And that will contain a int32 local IX, or I think I said local TX, right? For local TX, for tile X, yeah. So local IX would be wrong. Local IX is wrong, isn't it? Yeah, local IX and local IY is wrong. We already know it's, so let me go over here for a second. So if I type local IX, loc IX, so any of these that are wrong, use loc TX. Local tile X, right? So it's TX, not IX. I know this is kind of like stupid, but the thing is, I absolutely need to make sure that I have my variable names kind of like nailed down. So we need to make sure that we have very specific variable names that always mean very specific things. So local TY, local TX, local tile X, local tile Y, right? We don't have anything called IX and IY. It's already implied that if it's a tile coordinate, that it is indeed a integer value. So local TX, local tile coordinate X. Though local tile coordinate Y, right? So we got local TX, we got local TY. This is not correct because I don't know what I'm doing here. So int32, loc TX, loc TY, right? Okay. And also we need a semicolon at the end of the definition. So this thing here, let's go into the function where we have all the defines, right? So we kind of defined everything here like this. I don't know if that's where I want to put this. I don't know where I want to do this. Well, actually, you know, let's, when in doubt, maybe just P5D Tor. So go over here. We're just going to say, you know, struct. That's why I didn't want to do this, right? I don't want it to get too ugly. So let's just go right here. Define P5D Tor, right? And let's just put it right there, right? I think that's a good place. Undef P5D Tor, right? So P5D Tor, and then we can go like this. We can just say P5D Tor, P5D Tor, like that. I think that's a little bit better. So now that we have this thing here, we can... P5D Tor is going to equal this conversion where we take the exponent and the layer index and tile exponent and layer index, and we can convert it to this tile origin, right? And that means we need to actually create this function as well, so that sucks. So let's just put some gibberish here to make sure this does not compile. And then let's go up here and just create the helper function that we're going to need for this, right? So we're just going to say this is going to be return this struct type, right? So let's just take this and say that we're going to return this struct type, and it's going to take an int32 tile exponent, and it's going to take an int32 P5D Tor, right? And it's going to return the exact origin values that we kind of need for doing this, right? So let's kind of figure that out. So we know that the first part is the first part is going diagonal, right? So we got to figure out the diagonal, and then we got to move to the right or to the left, right? So we already have a helper function. I believe it's called OpenGL, and we take the tile exponent, converted to, I think, diagpix is what it's called. So I don't know if it exists in here, but it definitely exists somewhere. So let's take a look at that and see if we can find it. So exponent to... I know we have a function for something like this. It might actually be in the PAINT5D system. So if we look at PAINT5D, which is included before this system, right? So this is the OpenGL version of the PAINT5D system, which comes after PAINT5D. And we probably have a helper function that already does tile exponent converted to diagpix. So if we have it already, let's just throw it in there. So this is only going to compile as... Oh, here it is. Tile exponent converted to diagpixels. You're right there. Well, how come I didn't see that earlier? So we have it. So this little lookup table here. And so we can take that, and for this function here, oh, because it has this, it's because OpenGL PAINT5D, so some of these namespaces need to be fixed. But this was the namespace. Okay, so tile exponent converted to diagpix, right? So we take tile exponent, we pump it into here, and that gives us diagpix, right? So int32 diagpix equals calling this, right? And this diagonal pixel location, if we look at the diagrams here, PAINT5D data, diagpix is like either here or here, anywhere where these D's are is diagpix, is the diagonal, right? Okay, so now we need to say that for the output, right? So this output here, I don't know how we want to do this, so I guess let's put it right here. Let's say define P5D Tor struct and then that there, and then we'll undef it right here. Undef P5D Tor. Okay, cool. Okay. So let's make a variable declaration here. So P5D Tor, P5D Tor, right? So, and dot loc tx equals diag pix plus something something something, we don't know. And for the y, same idea, something something something. So depending on if we are is there a way to do this branchless? There's probably a branchless way to do this calculation, right? We could obviously do it in a big if-else. And you know what? Also, never mind. We're gonna do it just we're gonna do it in a dead simple way. So, I know there's probably a more clever, mathematically pure way to solve this, but we need to make our code dead simple, right? We can optimize this later. So I see there's kind of 3 people in here. So if you've never seen what I'm working on, you can take a look at my technical demos. I'm working on a fractal auto-tiling engine. I'm going to keep on going here. Usually I kind of give a more in-depth thing, but if somebody requests that they want to see a little overview of what I'm working on and me to explain it, I will. Otherwise, I'm going to keep on going here. So we got these diagonal pixels, and let's just say that, you know, if the layer, so this laydex, oh, hold on. I did not do that correctly. Tile exponent and layer dex. Okay, so we take the tile exponent and the layer index, right? So if we highlight this, tile exponent and layer index, and we convert it into this value here, this PAINT5D tile origin location here, okay? So if 0 equals the layer dex, then we don't have to do anything, right? It's one of these origins, and these origins here are directly anchored to the first layer of data, right? Now, so the diagonal right here, these diagonal origins, right? The top left origins for the different tile sizes, right? They're always anchored right here on the diagonal. So if the layer index is 0, we don't have to do anything. So we could say just add 0. There's no offset to be done. Okay. Else, right? And let's just do this two more times, right? There's 3 different layers. So bam, bam, and bad layer index year 2021. Let's just make a little notification here. Bad layer index year 2021. And if the layer index is 1 or 2, layer index 1 is going to be like right here. Layer index 2 is here, right? And then for the different tile sizes, you know, here and here and here. So now the thing is that with the with those different tile sizes, there's going to be different offsets, isn't there? Because the offset depends on what exponent you have, right? So what we can do is we could take we should have a function called we should have a function that is called let's put it over here actually. We should be able to take the tile exponent size, and we should be able to convert it into tilpeb, right? The number of pebbles, right? So if we take a look at this, we should have a function for this. Yeah, so we have a function for this tile exponent to pebbles, right? So if it's tile exponent 0, hold on. Oh, no, this is the pebble size, which is not the same thing as the max coordinate. So what we want is max coordinate, right? Max core. Yeah, maximum coordinate, 0 to 127 for the smallest tile, 0 to 63 for the larger tile, 0 to 31 for tiles even larger, and eventually for the maximum tile size, it's so big that the only coordinate it can be at is 0, 0. So that's actually the function that we're going to need to use. And so we're going to take this function, and we did not... What's the namespace on this? Yeah, so I need to get a more consistent namespace here. But we'll normalize the namespacing after we just get the code working, because this namespacing kind of sucks. The idea was to call it OpenGL because it runs as OpenGL, and then, right, so we still want 2 namespaces, so I figure OpenGL is the first namespace, and the subsystem it's for is the other namespace. But the tile exponent to the maximum coordinate, right? So we'll just take tile exponent, and we'll put it in there as well. And then we'll just say, you know, maximum coordinate equals this, right? And diagpics and max coordinate, I really want to kind of put everything in a section where we're kind of declaring everything. So right here, let's make a section called, you know, declare variables. And let's declare everything ahead of time, just because that's going to be a little bit easier. So here, 1, 2, 3, 4. And declare variables. Okay, so we're going to declare variables. And int32 diagpics. This thing here, we're going to move it over here. Okay, and int32 maximum coordinate. Layer dex. Okay, so once we have the maximum coordinate here, if we are on this layer here, we're going to take that diagonal coordinate and we're going to add the hold on. We're going to do... Right. So... if it's, if we're on this thing here, right, we have to add the maximum coordinate. So we started at this diagonal, we add the maximum coordinate, and we're at the last coordinate over here on this first tile. But we want to get to the first coordinate on this next tile. So that's why we need a +1. And then let's kind of steal this. And let's just swap this, right? So let's swap that. So, local tx. Now, if we're on the second layer, we want to move down, right? So we're gonna stay. We're gonna go from this origin here, and we're gonna move down to here, right? Or we're gonna go from this origin, and we're gonna move down to here. Or we're gonna go from this origin, and we're gonna move down to here, right? So that's going to give us the PAINT5D tile origin location, right? So this thing here, and then this function is called. Oh, hold on. God, I hate this name really clutters things up here. Can we just well, we've already done this to ourselves, so I don't know. This is very cluttery. I'm gonna I don't know. Yeah, I'm just gonna do this. I don't know. P5D Tor. I'm gonna just try to put it right here. That's kind of... it's better than it was. Right, that, just so I can read this a bit better, because when I glanced at it, I was like, what the heck is this, right? Okay. Yeah, so anywhere we have this P5D Tor, let's just, yeah, let's just, I know I had a define that defines it somewhere else. So this define here, let's get rid of that define. And did we use it? And we used it over here as well. So let's kind of get rid of it there as well. Right. And then we'll just undef P5D Tor here. That is kind of ugly. It's kind of ugly, but it's better than what it was, just because I want to be able to look at this and see it right away, right? So you got the tile exponent in the tile layer, right? And then we're going to convert it into this P5D tile origin, right? Tile exponent maximum coordinate, local TX and local TY are from in there. And the different offset depending on what layer we're on. That all looks good to me. Now we also have to remember to return the value. So right here we're going to, I don't know where we want to put the return. P5D Tor, right? PAINT5D tile origin, right? So now that we have this helper function, we can use it down here, right? PAINT5D tile origin. We're going to take the tile exponent and the layer index, and we're going to find out the origin of where that data is, okay? And, right, that origin depends on what layer it is, right? So if we look at this for a second, well, we're looping through the tile exponent, but where's the layer, right? And this ladex, I don't think this is actually defined anywhere, is it? Oh, it actually is, because we're going to... Got it. Okay, so that's defined. Tile origin. Okay, so once we have the origin of the data, we just need to... what do we need to do here? We need to convert the canvas user view IX, canvas user view IY. We need to convert that to a local coordinate, right? So we have found out the origin. So we could say get origin of block of memory for the current tile value that is being laid, right? So right here, that's what we're doing, right? We're getting the tile origin of the current block of memory that's being laid. Now, we need to get local coordinates. We need to transform. We need to somehow transform this IX, IY into a local coordinate value, right? So we have this offset here, but we need to convert it into convert IX, IY chords into local to data partition coordinates, right? So we need to somehow convert those IX, IYs into some type of local coordinate. And to do that, I don't know. In fact, I need to take a quick break, and then I'll kind of figure it out. But we know we're somewhere over here. We got to figure it out. Shouldn't be too hard, but I do need to take a break, so I'll be right back. I also need to do more push-ups and whatnot. If we look at our push-ups, so I'm going to take a quick break. I'll set a timer. I'm going to say a 15-minute break so I can do a little bit of exercise as well. Oh, actually, this is the wrong thing for that. Yeah, I'll do a 15-minute break. I'll be back. But I'll do some exercise to try to get more push-ups in. Okay, so I realized what needs to be done. It's pretty simple to get this working. So right here where we have, we're taking the int x, we're taking the ix, iy coordinate, which is the canvas user view coordinate, which is down here. We need to localize that coordinate, right? So that's coordinate is anywhere in here. We need to localize it to one of these blocks. And then from there, we can do some pretty basic tile map math to figure out what tile we're setting. So this thing right here, this origin x, right, which is 0 or 1, right? So what I want to say, I'm just going to say, I don't know what I want to call it. It's like oh, you know what it is? It's, so what we're going to do is say, okay, yeah, so pebble, tx equals, the ix value here. All right, so let's take the big thing, right? So the canvas user view x, okay, and we're going to subtract this value times 128, right? To localize this coordinate in terms of local to this block, local to this block, local to this block, or local to this block. To do that, we just need to take the input coordinate on this canvas user view. We want to take the input canvas user view coordinate, and we're going to take the tile quadrant. God, that's not quite correct. We said OX for this is the origin X. This is origin X. Okay, let's call this QX. Origin. This is origin. This is quadrant. Yeah, let's do that because this is like a quadrant value, right? And it's either 0 or 1 right here. Quadrant X, quadrant Y. And right here we're multiplying by that quadrant, right? And then the tile quadrant do we want to call it origin X or offset? I guess origin X works. So origin X equals, we're going to take this, it's either 0 or 1, and we multiply it by 128, right? Okay, so this right here, and then we can assert that this is, this is going to be greater than or equal to 0, and it's going to be, oh god, sorry. And it's going to be less than or equal to 256 minus 1. Well, actually, it's going to be, the origin actually is going to be like right here, so actually it can be bounded between 128. Right? 128 is the other origin. So it's actually going to be, we can just do 128. That'll work. the more we can kind of nail in the range of these, the better. So yeah, this is between... Okay, so let's just color code this, make sure that this is correct. So, okay. This is the quadrant location. This is the origin location. I got those a little bit confused when I was doing these calculations. So the pebble tile X location is going to... We're going to take the quadrant location, which is either a 0 or a 1, and we're going to multiply by 128. Oh, wait, we're already multiplying by 128 here, right? So we can just take the... We can just subtract the origin, right? So we can... To localize this, we actually just... Instead of doing that over again, we can name what we're doing right here. So we're actually subtracting the origin location there. So the X value, right? The pebble X value and Y value, right? Same deal. So let's look at this again. So here's the X values and the Y values that we're using. Okay, everything looks correct there. So we're just going to subtract the origin to zero out these values. So these two values right here are any value somewhere mapped onto here. And we want to get that value local to here, local to here, local to here, or local to here. And once we have that, it's really easy to nail down the other coordinates. So let's put this... I don't know where we're going to put this. int32 peb tx. And this is pebble tile X, int32 peb ty, and that's going to be pebble tile y, right? So the pebble coordinates are these, and so these are the coordinates in terms of the smallest possible tile. So we're going to get a local coordinate that's in terms of the smallest possible tile. Because remember, this canvas user view is these coordinates right here are in terms of pebbles, right? And now, to convert the input to a local data coordinate, all we need to do is figure out the size of a pebble. So now I think we just call it tilpeb, right? I believe that's what we called it. So I think we have some function that's going to be called a tile exponent converted to tilpeb, right? And let's take a look at that, because I'm pretty sure we have that. Yeah, tile exponent to tilpeb. And so it's the size of a tile in terms of pebbles. So the smallest tile is 1 pebble in size, right? Because it's our unit size. The next tile size up is 2 by 2 pebbles. The next tile size up is 4 by 4 pebbles, etc., right? So this function right here is what we need. And let's go back to where we're about to call it. And since we're calling it tilpeb, we might as well, let's say tilpeb. If we go tilpeb, right? So tilpeb, yep, that already exists. And we'll just put the tile exponent right there and just go like that. And then we'll just say, you know, tilpeb equals. So we're kind of doing it in a kind of a Pythonic kind of indentation style here. And once we have this location here, now why do we have this? What is this for? What is the usefulness of this? Oh, get the origin block of memory for the current. Okay, so this is in terms of the data view, right? So this this tile origin here is in terms of the data view right now, but as far as this, this tile pebble size, we're looking at this data to get that. So to get this, now that we have the tile pebble, to get the local x and y, so we have somewhere we have a I don't know what we're going to say here. So loc tile x, right? So the local tile x location is going to equal we're going to take this pebble right here. We're going to take the pebble coordinate, and we're going to divide by the size, right? So if we're looking at the if this tile exponent is 0, then the size of a pebble is 1, right? So if we divide by 1, we get the exact same thing out. Now, if we're on tile exponent 1, then the size of a pebble is 2 by 2 pebbles. So that means that this has to be 0 and 1 divided by 2, both give us 0, right? And then once we get to coordinate 2 in terms of pebbles, then this will give us a 1, and the local tile x will be 1 because we're on the next tile, right? If that makes sense. I may have not explained that correctly, good enough, but I understand it, so that's good enough for me. So we'll take the pebble x, pebble y, and we get the local tile x, local tile y. Okay, so now int 32, local tile x, int 32, local tile y. And let's actually say local tile x or y chord. And actually, let's kind of like make a little video ID of this. So at video integer ID, and it's video 105, and the time is at 6 hours, 38 minutes. Let's just say 6 hours, 38 minutes. And let's look at the diagram. So the local tile x, local tile y is some type of local coordinate, like say here, or a local coordinate in one of these blocks, or any local coordinate inside of one of these blocks. That's what the local tile x, local tile y means. The pebble tile x, tile y is a local coordinate local to somewhere in here, or a local coordinate local somewhere into here, or local somewhere here, or local into here, right? And the canvas user view IX, canvas user IY, that's a coordinate that is kind of like global to this entire mapping right here, right? So I just wanted to describe that a little bit and put a little timestamp so that the video kind of like helps describe things a little bit better, right? Okay, so with the local TX, local TY, let's see what else we got to do here. And also, let's remember what we're doing here. So we're kind of putting bits, right? We want to put these bits, we want to unpack them and put them where they belong. Okay. So local TX, local TY. Okay, cool. And this is going to be this is going to be kind of tricky, right? Because for every single pixel, we're going to have to unpack the value. And I feel like we already have a utility function we can use for this in PAINT5D. So let's look at the PAINT5D functions for a second, because I think PAINT5D should already have a function we can use for this that's already been written. And I really don't want to have to write this again. So let's kind of look for a put function. Like if we've been consistent with our naming, we might be able to, let's do a underscore put and see if we can find some type of put function. And let's not go backwards like that. That's going to annoy the heck out of me. So Bitpacked put. So this looks about right. We got the bitmap we want to put the data into. We have the global component index, the offset index, and the tile value. So there should be some type of wrapper function for that that'll be a little bit more specific. So let's see if we can find that. Where are we? Bitpacking stuff, blah blah blah, blah blah blah, a whole bunch of complicated stuff. Oh god, this is PAINT5D put. Tile quadrant, tile exponent, tile layer, local TX. This is what we need, actually. So let's steal it. Let's steal this function, because that's what we're going to use. Okay. And And this is already pretty well tested, so I don't have to like worry about it, right? I can just... And now this is not a OpenGL flavor function, but it doesn't matter because this specific function is never going to be compiled as OpenGL code. And so let's kind of look at what we have here. What do we have that's already set, and what do we need to define here, right? So let's first of all, these are all UO8 values. All values are UO8 here. But that's okay because we are not compiling as OpenGL code. Okay, so that's fine because we're not compiling any of this to OpenGL code. But we might... Let's not worry too much about what's going on. Let's create the shorthanded versions, and then we'll kind of like search for everything and be like, hey, we also use layer, tx, ty, this is AD, and this is tile value, I guess. And let's just remove that because I actually want to have enough room to where we're not going too far over to the right. Okay, so now that we have this, let's just kind of color code all of these and kind of see what is missing and what's not missing. I don't know if that's really going to help me. I think that might be the wrong way to go. I think that's the wrong way to go about this. We actually want to do it the other way around, right? So we want to look at all of this stuff and be like, what is here? So we have the layer index. Okay, we have the offset index, so that's good. The tile value needs to be extracted from here. Okay. But these two things, the latex and osdex, oh, we called it... Oh, okay, got ya. So this is, right here is latex, right? So this is the layer index, right? Layer index. So I have some fractionation of my variable names, but I see why I did latex and osdex, because then we could... That's fine. It's a little bit fractionated, that kind of sucks, but... and the offset index is 0 to 15. And I'm not really a fan of what's going on here. Let's just call it lay and os, right? We have a shorthand for that. Let's just call it lay and os. That's fine. Lay, os, and local tx, local ty. We just defined those, right? So we have those. The tile value we need to extract, but once we have it extracted, we'll just call it tile value, right? And the quadrant... Let's think about quadrant. The quadrant tile exponent is TE, right? We have, if we look at tile exponent right here, we should have a tile exponent, right? Or do we call it tile exponent? TE equals, oh, so we made a mistake here. So we have defined tile exponent like that, so we can capitalize that if we want. We can actually put that there as well. So layer, tile exponent. Now the tile quadrant, so let's think about where is tile quadrant? Is that, did we already define that? Let's look for that. Tile quadrant. So tile quadrant, QX. Okay, so for the quadrant, we need to do an index to xy calculation here, right? So we have the xy. So we need to do an index to, or xy to index. Xy to index C99, right? We got to do a C99 index to xy coordinate, xy conversion function. And we're going to call it tile quadrant, right? The tile quadrant, 0, 1, 2, or 3, right? And yeah, okay, I was just making sure. The offset subtile quadrant index, yes, that's correct. So this x value is going to be this qx, right? So this qx, and this is qy right here. So this is qy, right? So it's going to be the x is the remainder, and we need to say that it's going to be 2 here, right? Because 2 is, all right, let's try to, right, so 2, because it's a 2 by 2 tile map, essentially, right? Like if we look at this, right, this is 2 by 2 cells, hence why we need to multiply by 2, and then add the remainder, right? So this is how many full rows do we have, right? And each row is has 2 on the x, right? And then whatever's left over, if that makes sense. But anyways, this is the correct formula. I'm absolutely sure of it. So we could make a note here. We could say xy to index formula for 2 by 2 cell grid, right? That's what's going on here. We also want to make a note of this, right? So we'll do int32 a 1D index of tile quadrant OX, tile quadrant OX, OY, right? That's a horrible comment. 1D index of tile, I don't know. It's a one-dimensional index version of a previous variable, whatever. Let's do a video ID of this. Don't forget about making a long comment. So we're at 105, and the time, let's condense this a bit. It's video 105, and the time is, actually, let's keep the number the same, just so that we can control F and find all the comments from the same video. The time is 6 hours, 51 minutes, and 10 seconds. Yeah. So right here, let's describe this. This is the one-dimensional index version of the quadrant X, quadrant Y location right here. That's what this is. So that means that this calculation needs to use QX, QY. So let's make sure it's using QX, QY. So actually, let's erase everything for a second. Oh, it looks like more is highlighted than I wanted, but this should use, yeah, QX and QY, right? The quadrant location to get a index, right? So we're going to take the XY cell or quadrant location, and we're going to convert that XY location into a quadrant location, right? So now with this tile quadrant location, CTQ, now we have all the variables that we need to satisfy this. Well, actually not quite, because tile value has not yet been extracted, right? So if we look at this, actually we got to work backwards, right? We want to go local TX and local TY. That's colored, right? Now, where's layer? Where is layer being defined? So layer, where are you? So layer is this guy, right? So that's an input parameter right there. So that's fine. We got that. What else do we have? So we have the tile exponent. So let's go find tile exponent. That's TE. TE is actually what we're looping through here, right? So tile exponent is covered. Now is tile exponent declared up here? Yes, it is. So what else do we got? We got this offset thing. So offset is, I believe, an input parameter. So if we go up here, we can see this offset dex thing here. So osdex, which has a define as os. And if we look down here, that should now be colored, right? So os is colored. So we got this tile quadrant thing. Where is that accounted for? It's accounted for here. So if we highlight tile quad, and then we highlight the variable it's derived from up here. And that is derived from this IXIY. IXIY is an input, right? It's shorthand for this thing, this variable right here. Okay? So we absolutely know that that is accounted for too. So everything's colored except for this tile value, right? So tile value is the last thing we need to figure out here. So let's look at tile value. And tile value is not supplied. It needs to be, we need to kind of look at these bits, and we need to extract it from this B16 here. So let's take the long-handed version of this variable for now. And let's kind of unpack what we need to set, right? So it's going to depend on the tile exponent for what we're going to set here. So tile value equals, we're going to take the 16 bits and we're going to shift it over by tile exponent times 2. Okay, so the least significant bits hold the lower tile exponent tile values, while the most significant bits hold the higher tile exponent values. So all we got to do is shift it out like this. Now, when we shift it, we still have to mask it, right? Because if we don't mask this, then if we don't mask it, we're going to get values that are out of range, right? So this needs to be masked with it's a 2-bit value, right? So I'm going to call it bin011. That's what I've been calling it in a lot of other code. And then somewhere we got to like put a define for that. And I think I'm just going to shove it up here with some other stuff. So define, right? And this is going to be 3. So binary for 2 set bits is going to be that, right? So then right here, we could make a little checksum here. And the first thing is actually not a checksum number. It is kind of a define thing. So 1 and 2 right here. And then beneath here, we're going to say undef bin001. And then we'll make a little checksum here as well. And this thing will be, we'll do that, and then like that. Yeah, like that. That looks good. Okay. So now the tile value is extracted. We can also assert tile value is greater than or equal to 0, and the tile value is less than or equal to 3, right? 0, 1, 2, or 3, right? Those are the only values we can have. Because that is the range of values if we're using a 2-bit value, right? So, 2-bit mask. So that's a 2-bit mask right there, and we're shifting out the tile value, right? So the tile value here. So now we got to say, well, does that all make sense? Because that should be everything we need to do to get this working. So let's kind of look at this and sanity check ourselves here. So anytime we want to, let's read the function name. So canvas user view pixel to cov bits, and it's a put function. So anytime we want to put something down here, we have to target a certain layer, right? So The payload is specific to a certain layer, right? Because if we try to target all layers at once, we wouldn't be able to do that because 8 tile sizes in 3 layers is 8 times 3, which is 24. Wait, hold on. What am I missing here? That seems reasonable. Hold on. There was a reason. And now I'm kind of like, why did I do it that way? Because now I'm like, 8 times 3, 8 and 8 is 16. Add another 8, you got 24. What am I missing here? Because I thought that that's enough bits to fit into a 32-bit integer. So why did I not do that? Okay, let's look at the data again. So we're going to target a certain layer. We're going to target a certain tile size and layer, right? So there's 8 tiles here. 8 here. 8 different tile sizes. 3 different layers. Oh, what I'm forgetting is that... Okay, so we have 3 different layers, and we have 8 different tile sizes, and yes, 3 times 8 is 24. But remember, we also have to have the payload for the tile values as well, right? So the tile values are 2 bits. So 3 layers times 8 for 8 different tile sizes, that gives us 24, but then times 2 for 2 bits per tile value, and now we have 48. Now we've exceeded 32 bits. Okay, so that makes sense. So anytime we try to set a cluster of tile values, we have to target the layer as well as the offset dex we want to set on, and then we want to give it a payload, right? This payload is going to define all 8 tiles of all different 8 tile sizes for a specific layer and offset dex, and its physical location is going to be mapped in terms of the canvas user view global coordinate, right? So it's going to be mapped in the coordinate where it's going to go is going to be mapped in terms of this. But in terms of what data we're setting, this is the data we're setting, and this is the location where we're setting it, right? If that makes sense. So this is so this right here, location of the data. Right, so this is the location of the data. And these variables here are the values of the data. Right, so this is roughly speaking, right? If we want to segment the inputs, the way these inputs are divided, that's the way we would be rolling with that. Let's not do that. These two would be the locations of the data, whereas these 3 variables would be the actual values of the data. So the one thing I'm concerned about is, are we using this properly? So let's color code this for a second. I want to make sure that I'm using this correctly. And I see we have another person that dropped by. I'm working on a fractal auto tiling engine. You can always check out my technical demos. I'm gonna put it in the chat, but I'm gonna keep on going here, unless you request. If you ask me a question, I will answer. Otherwise, I'm gonna keep going here. So let's just make sure that this is proper here. I think it is, but I want to double check this one more time. So I'm concerned about how we're targeting the values. So we're gonna take the tile value somewhere. We're shifting out the tile value, right? So we're iterating through every single tile exponent, and with that we're going to shift out the tile value, get the tile value, and then we're targeting a certain auto tile set. Yeah, that all looks good. That all looks good. I think that okay, so we're ready to just give this code a run, and what we're going to do is we're going to give the code a run, and we're going to fix some syntax errors, and then once we can get the code actually up and running, then we can visually verify to see if indeed we are setting the pattern we think we're setting on the data or not. And so this will be kind of fun. So let's hope this. I'm sure I've made plenty of mistakes, but we'll see what they are. So bin 011 is redefined. So I think that maybe bin 011 might actually be defined at the top level. And yeah, so we defined that at the top level, and that's fine. If we want to define it at the top level like that, I'm totally okay with doing that. So let's go back to where we define it over here, and let's just kind of remove it. So it was one of those things that was important enough that we defined it for the whole file. That's fine. And let's make sure that that is actually being undefined, right? So it is being undefined. I'm fine with that, right? And so there may be other things that we may have been redefining, but let's just go through it and see what else we got here. So tile exponent, we just kind of spelled that wrong, right? We want to normalize our variable names to reduce the mental search space. So yeah, tile exponent just needs to be tilexp. And is tilexp by any chance a value that needs to be... so we got this thing here. We might as well explain what that is. Paint, so P5D Tor, PAINT5D tile origin, right? And the tile origin, this is the origin pixel in terms of the data view, aka the texture memory storing the tile values, right? And let's make sure that that is correct, that that is what it is. So P5D Tor, well, we got the local tile X, local tile Y. I'm pretty sure from looking at that. Let's look at that in some other places as well for a second here. So P5D Tor, let's see where it's used. Tile exponent to P5D Tor. We're going to take, this is the output, diagpix max coordinate. Yeah, this is definitely what that is. X, Y. Okay, that makes sense. Diagpix plus the maximum coordinate plus 1. That looks good. We could also, while we're here, let's do an assert here. So, in terms of this output coordinate, if we look at our data view, right, this is a 512 by 512 partition, so we automatically know that when we're asserting this, we need to assert that, well, the very basic thing is p5tor.local tx is greater than or equal to 0, right? That's the easy one, right? It's never negative. The other thing we want to assert is that it is going to be less than or equal to 512 minus 1, right? Okay, because the maximum coordinate on the memory is 511, 511, right? Because it's a 512 by 512 block of memory, and the first pixel is addressed as 0, 0. So we can do a little assert here to make sure that these calculations are okay. Now, actually, if we really want to get pedantic about this, you see how everything is partitioned in these blocks of, we have 3 layers for everything, right? 3 layers, like every single time we're addressing something, it always has 3 layers. Well, guess what cannot be split into 3? The very last pixel. The very last pixel cannot be split into 3, which means that 511, 511 will never be touched, right? So, so if 512 minus 1 equals this thing, And we'll throw an error. Right, so there's no possible way that this can be a valid coordinate in terms of data, right? So the configuration pixel is never a valid location for storing data, right? So actually, there's actually, if we really want to be picky about this, there's actually 4 configuration pixels, right? That is getting very verbose. But if we think about it, there is all the way over here, but there's 1, 2, 3, 4 configuration pixels. So we have a... So let's go corner by corner. So at 256 minus 1, there's a configuration pixel, right? Then over here is a configuration pixel, so 512 on the X, but 256 on the Y. Then this one over here is going to be on the X, it's going to be the 256, but then it's going to be 512 on the Y, and this one's 512, 512, right? So let's color code that really quick. So nothing should be the same. So this is all cyan, this is all orange, and then these ones are mirror images of each other, right? And this is X and Y, so X and Y are colored. Okay, so any of these situations are invalid, right? Because we'll just we'll mark this and just say that, you know, error if on config pixel, right? So if we're on the configuration pixel, we're at an invalid coordinate, right? 1, 2, 3, 4. So let's take this and kind of section off this as well. And that gets kind of ugly and verbose. But at least it's correct. Code correctness we care more about than, oh my god, it's a whole bunch of code. Like, yeah, it sucks that it's a whole bunch of code. But oh well, right? So this is the core logic. Core logic of function, right? So this is the core logic of the function. So if we want to, maybe we want to make this section a little bit bolder just to get our attention. That way, you know, because there's a lot of clutter, right? There's all this clutter, right? We got this function. We have this function, but then the main logic we really want to look at is like right in the middle here. And then everything else is all this kind of like distraction, all these asserts and all these other things. And that can kind of suck. 1, 2, 3, 4. Yeah, so that looks good to me. Course range check, right? So this is a range check right here. Okay, so we got a range check. Excellent. Okay, so now, I kind of lost track of where we were, but I know that we want to get this compiling, right? So we're going to do whatever we can do to fix up the code to get it compiling, and then we're going to try to visually verify that this code is working correctly by running the unit tests and then checking the file that gets saved to disk. Right, so we're going to dump out the memory, right? So this represents texture memory, and it's a 512 by 512 block of pixels. And since we're encoding all of our memory in terms of pixels, it makes it really easy to visually debug things if we do things meticulously enough, right? We can write our tests in such a way that we can visually verify the tests are running correctly by dumping the memory to a PNG file and just kind of seeing, hey, does that look correct? So that's kind of what we're kind of getting to here. So let's give that a roll. I have good feelings about this, but it may take a lot of kind of like, there's probably a lot of stupid things that I have made in terms of mistakes that we're going to have to fix. Now, I think that it's better to, right, I'm not using any IntelliSense, so I'm making some stupid mistakes. But the thing is that I think that this encourages me to write better code where I'm not sloppy. And also the thing is sometimes those red squiggles really distract you while you're coding, right? So, like, these mistakes aren't mistakes in the general logic, right? They're like more fine-grained syntactical mistakes, and when I'm trying to program the overall algorithm, I don't care about small mistakes. I care about getting the overall algorithm correct, right? So let's, anytime we make a mistake, though, we might want to just double-check really quick and make sure we haven't made any transposition errors. So the offset X, offset Y is in terms of pebbles, I believe. This is a global coordinate, and this is the offset. That gives us the pebble tx, pebble ty. So this is a local coordinate on the extreme left. And that is talking about taking this input coordinate right here. So this is the input coordinate we're talking about, somewhere over this data set. And then we're going to subtract the origin. So this origin here on the extreme right is this origin here, here, or here. And we subtract that, and then we get a coordinate that's local to here, local to here, local to here, or local to here. So that looks good. Doesn't look suspicious at all. These things are things that I want to make sure are absolutely correct. I used a snippet, so I'm pretty sure it's right. So the y quadrant times 2 plus the x leftover gives us a 0, 1, 2, or 3. But do we have any assert function? No, we don't have an assert for this, so we should have an assert. We should have a sanity check here, though. So assert that tile quadrant is greater than or equal to 0, and tile quadrant is less than or equal to 0, 1, 2, 0, 1, 2, or 3, right? So we could do 4 minus 1 to make it more obvious that there's 4 quadrants. And the other thing I realized while I'm kind of like cleaning stuff up is this function, all the values should be 8-bit integers, right? And none of these inputs are 8-bit integers because we programmed this with the GLSL code in mind. However, if we go all the way up to this section is not compiled if this is OpenGL code, right? Because this was just a helper for us to test the correctness of the code. So we're going to go back down. Now there's implicit type conversion, so we shouldn't really have to do this. However, right, we're going to assume that everything here is in the correct range, and as long as everything in here is in the correct range, then all this will work properly. Now, yeah, this PAINT5D put probably has like a range check on it as well. So let's go in here for a second. So if we look at the PAINT5D functions, and you look at this PAINT5D put, yeah, we already have a bounds input checks on like all of these things. So we don't have to worry about these, right? So if these values are somehow out of range, we already have I have a check that's going to catch that. So I'm not too much worried about that. Okay, so now let's kind of try to compile that and see if we've made any more mistakes, and then we're going to keep on going. Tilpeb is undeclared. Okay, so let's find that. Tilpeb is the size in pebbles, right? So, right, so tile exponent to the size in pebbles of that tile, right? So we're going to convert the enumerated tile exponent to a size in pebbles, and then we do this tile map math, pretty simple tile map math to get a local tx, local ty, right? So local tx, local ty, should not exceed the maximum coordinate. Now, where is the maximum coordinate? Do we have a variable for maximum coordinate? Let me highlight this really quick, because we could bounds check this if we had the variable for maximum coordinate. And I feel like somewhere we might have it. Doesn't look like we have it, so what we're going to do here, let's assert that the local tile x is greater than or equal to 0, and loc tx is less than or equal to, so the local tx should always, according to our diagrams here, local tx, local ty should always be less than 128 minus 1, right? Always. No matter what the tile size is, it should always kind of be bounded within here at the very least. Now, this is a very coarse bounds, but also, we can also further bounds check. Local tile exact bounds check. So we could take this. Let's go 1, 2, 3, 4. We are a little bit outside of our column limit here because the code here actually needs to be indented 4 spaces away from the border. 1, 2, 3, 4, because we want to cut and paste it. And I keep on forgetting about that in some places. So in some places, 1, 2, 3, 4, like this is not correctly indented. Set all 8 tiles. I'll just call this set all 8 tiles instead, so that we can indent this properly. 1, 2, 3, 4. And set all 8 tiles. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. That's fine. Oh, we're a little bit out of room here. Let's just indent this like that. And 1, 2, 3, 4. Assert. I believe we have an assert macro, so let's just use that assert macro there to kind of like... And this is 1, 2, 3, 4, so this is already indented enough. Okay, so we need a int32 max core maximum local tile coordinate, right? Max core is the maximum local tile coordinate right here, and we can use that to further bounds check the local tx, local ty. So we can say max core equals the tile exponent. We can take tile exponent converted to max coordinate, right? We have a function for that, and so tile exponent, we just have a macro for that, right? TE is like a TE, right? Tile exponent, we can take that and we can just throw it in here like this. And we need the proper namespace for this. So let's kind of, I'm going to have to, so it's called OpenGL PAINT5D. Go backwards. I'm going to kind of clean up that namespacing. And, because right now this file, I want to keep it as the namespace of this file, I think. I don't know. I think that would be the proper thing to do. Yeah, so the tile exponent converted the max coordinate. So now we know that if local tx is greater than this maximum coordinate, or the local ty is greater than the maximum coordinate. If either of those cases happen, we have a problem on our hand, right? So we'll do an error, and we'll say loc txy oob 2021 0125, right? Just put a little date marker on that to make this error message a little bit unique. Okay, so now we have a ridiculous amount of error checking in here, but like I say, a solid foundation is the most important thing that we want in this code, and the prettiness of this code is not as high of a priority, right? So being able to understand the code. So in order of priorities, there's more priorities, but if I want to order 3 priorities really quick. First priority, always working code. Second priority is to be able to easily understand the code, easily make our way around the code. Okay, and the third priority is to have like a visual cleanliness that allows us to easily see if the code is correct, right? So, okay, yeah, let's give this a run and see what else we're missing here. And every time we find that we're missing something, we're kind of going to go into the code and be like, hey, we're missing this thing, let's add it, and then let's also add even more code to check ourselves, right? So anytime we see that we've made an oversight where we've like forgotten something, we're going to look at that code again a little bit more carefully and be like, hey, is there anything else we're missing here? So the tile size in pebbles, we have this tile exponent converted to tile pebbles. That is the correct call. And let's assert, yeah, so let's just assert that till peb greater than or equal to 0 and till peb is less than or equal to so the largest size in pebbles is 128, right? So if we look at the diagram, this is a 128 by 128 section, right? And this is for the smallest tile. It covers 128 by 128. The smallest tile is pebbles, and so this is 128 by 128 pebbles, and the largest tile therefore can be 128 by 128 pebbles in size. Therefore, the size in pebbles needs to be between 0 and 128. So we're just going to make sure that that's correct. And then till peb doesn't look like it's been declared, so somewhere in here we just need to declare that. So let's just do int32 and till peb. And we'll just say tile size in pebbles, right? That's what that is. So let's make a little description. Let's keep on doing kind of video integer IDs of this. So 105, and the time is, what time is it? The time is at 7 hours, 25 minutes, and 35 seconds. Right? Okay. Let's describe what's going on here. But first, let's make this 26 minutes and 0 seconds because I kind of had a delay there. Okay, so let's describe what tile pebble is one more time for the camera. So tile pebble means tile size in pebbles, and a pebble is the smallest possible tile value. So in the data view, this is a data allocation for the smallest tile size. And this data allocation is the largest subsection we can possibly have. And the reason the smallest tile has the largest allocation is because you need more small tiles to cover the entire canvas than you do large tiles, right? So you could think of the small tiles as grains of sand, right? If you try to cover a floor with grains of sand, you're going to need a lot of grains of sand. Therefore, we have a lot of data for that, right? Whereas if you try to cover the canvas with a gigantic stone tablet that's gigantic and huge, right? You would only need like one of them, right? So, if that makes sense, right? So the largest tile value is just 1 pixel, or technically 3 pixels, because you can have 3 different layers. But let's just say that the largest tile value is like 1 pixel here, or 1 cluster of 3 pixels right down here, way down here. And that's because you can only have 1 tile of the very largest tile size, because it like covers all of this. And the largest tile size in pebbles is 128 by 128 pebbles. Okay, so anyways, just describe that for the camera again. I know I've described a lot of this over and over and over again, but the thing is that there's hours and hours of footage, so it makes sense to kind of describe things over and over again. It also gives me practice to explain this again and again and again. So the first thing I'm kind of noticing here is this does not look justified. Let's justify that to make it consistent with everything else. And tile value, so we're inside of, so this is OpenGL hack code and fragment shader, so we're in this file in 835. So let's look at 835 really quick. 835, the tile value. We're extracting this tile value from the bits. Remember, every tile value is 2 bits. The tile values for the lower tile exponent values. So if the tile exponent is 0, it's going to be in the least significant bit position, so we're going to shift by 0, right? 0 times 2 is 0. And then we're going to mask those 2 bits out, right? And then the tile value for the highest exponent value is going to be 7 times 2. That's going to be 14. We're going to shift over 14, and then we're going to mask by 2. So that makes sense. And then we also can check, right, that's going to make sense. Yeah, that makes sense. Tile value looks like we forgot to declare it. Now, tile value should be so first of all, this needs to be unsigned. Anything that is colored right now needs to be unsigned. So let's go up here for a second and make absolutely sure that is the case. So B16, yeah, unsigned, right? So the tile value, like all these things, are signed. Let's put this over here. Or I don't know. I just want to make a note, because one of these things is not like the other, right? Like, all of this is the same, but this thing is unsigned, right? So I want to make absolutely sure that I do not accidentally make this int32. 2-bit tile value to set, right? So there's a 2-bit tile value to set right here. This is what that is. I'm good with that. Let's remove some of this extra spacing. And hey, so I don't know who's here. I do not check my, what do you call it? I know there's some way to get a viewers list. I don't check it. So anytime I see more people, I'm just going to shove my technical demos. And if you have any questions or you want to ask me anything, like seriously, just ask me anything, I will answer. You know, if you ask me something very personal, maybe I'll give you a no comment. But besides that, you're good. You know, try not to say anything that would get my channel banned. Really, I don't care what you say, though I do want to make sure that I can continue streaming, so try not to sabotage me. But besides that, yeah, just say anything. Like, you know, I don't care. You could ask me a personal question about something, and then, you know, if I don't think I can publicly answer, I can always direct message you, right? So even if your question gets kind of inappropriate, if I think I can answer it, I'll answer it, even if I have to answer it in private. So I just want this to be kind of a place where you can say anything that's on your mind. Though I do want to keep it kind of to programming, but like I'm not really gonna get angry if you ask me something like way off in left field. Okay, so Let's, Oh, wait a second here. This has to be indented, doesn't it? We have some problems. Everything here is almost indented correctly, except then we get over here, and it's not. So let's look at this for a second. Yeah, so we can kind of do that, and then maybe... this is T. Let's try to compress all this. And let's try to just close this off nicely so that when we're looking at this code, we can kind of see the border, right? So the border of this is inset by 4 spaces, so it's not like most of the code we write, because we want to be able to cut and paste it into a shader string and wrap quote marks around it. So it's a little bit different than the code we usually write, right? We want to inset a little bit over on this side so we can put it in a shader string. Okay. So PAINT5D tile origin, right? And tile origin is the origin on the texture memory storing data. So that's what this is. Let's make sure that's what that is. So let's look at this. So the layer index converted to P5D Tor, tile exponent, layer dex. Pretty sure that's what it is. Okay, yeah, let's give this another run, see if there's anything else we're missing. Oh, so this tile value, we can't do that kind of check, can we? The tile value is unsigned. So let's just not deal with that. Let's just say less than or equal to 3. Also, over here, where we do this craziness, P5D Tor is a thing that has, like, a local IX, local IY, right? So what the heck here? Hold on here. So here's local TX, local TY. And that's good and all. So somehow we've decided, hey, let's calculate this thing. And then we never actually use it. And why is that? Now, is it because our helper function kind of like did what we needed to? So this is the origin. Yeah, this is the origin on the memory, right? And it turns out that we have this helper function, which we just give it the local TX, local TY here, and some other stuff, and the tile value we want to set, and it's going to manage all that for us. Tile exponent and the layer index. So it looks to me like I got ahead of myself and I made this helper function, and it turns out that I don't actually need it because this thing here. So what we're going to do here is I get what this is for, but it looks like we do not need it. So we're going to comment it out. We're just going to comment it out and try to... God, this is very long. We made this whole function. Yeah, let's just comment it out. And... because we don't actually need this one. My bad. I see what's going on here. It's if we didn't have that, if we did, I coded this before I realized, hey, you know what? I can just use this helper function that I already coded. So we're gonna use this because it's already kind of well tested. This function's already well tested, so I don't want to have to recalculate things that I right. If I have to recalculate, all the things that I have to recalculate are potential mistakes, right? So I want to use that rather than use this new function I made. We won't delete this function I made, even though it's a helper function that was specifically for the function we're currently in. And, yeah, I mean, yeah, so let's, okay, so we have that, and that means that this P5D Tor thing we came up with, we don't need that anymore. It's nice that we came up with a concept for that, but we don't need it, do we? So, I don't know how we're gonna do this. Actually, no, let's not do that. Let's do this. Let's just put this over here like that, and let's kind of mark it out like this. Okay, there we go. So we just mark that out. Mark it as deleted, right? So a lot of times I won't actually delete code, but if I explicitly say, you know, I thought about it and I realized I don't need it, then I'll kind of like do this to it, right? I like to kind of make note of what I do and then make note of what I don't do as well, if that makes sense, right? So, anyways, let's give this another shot, see what else we're missing, and UO8 is undeclared. So UO8 is not declared because this whole file we're in isn't supposed to know about 8-bit integers because it's supposed to be compiled as GLSL code. However, this specific section is only going to get compiled if it's not OpenGL. So we could kind of like go up here and just go define, let's go define UO8 right here. And then we can make a note that we have 2 macros for this section, and then we can go down to the bottom of this section here. All right, so all the way down here. And we can undef the UO8 value, right? So this unsigned 8-bit integer, we can undefine that here. And this is a mess, but whatever. We'll get this working. So, okay, so it's compiling. That's good. And so we're gonna hope that we don't have any like runtime assert problems or anything. Okay, so cool. So this actually failed at the current unit test that was failing yesterday. So that means that we successfully ran the test we wanted to. We successfully ran some other code now. So if we look at here, we have this thing here, I believe. Yeah. So let's just close this for a second, and let's cross our fingers because I'm hoping for some good things here. So let's go look at this output file and see what that looks like. Come on, come on, come on. Oh, nice! Excellent! Excellent! Exactly what I wanted to see. This is exactly what I wanted to see. So you'll notice a slight difference between, right, this file and this file, right? So these both look how I want them to look for what I've been doing. But the reason why this is white is because we're targeting every single offset index, right? So we're packing 16 different auto tile sets into this texture memory, right? And we're slicing up those 32 bits into pairs of 2 bits, and every single slice of the pixels, every 2-bit slice of the pixels of the bitmap is a different auto tile set. And we iterated through every single auto tile set, and we set we used a payload. We used a payload for tile values that would result in everything being white after we iterated through everything. Let me show you. So the reason why that's all white like that. Let's go find that. So let's see if we can find the code we wrote for this. So it's the put function. So we have this get function, and we wrote this put function, right? So this is our put function. And let's try to find this. It should actually be in the function file here. And if you look here, we see this put function. This is where we're calling it. And we use we start with we're using this canvas user view location. We're trying to go around the border of here using all tile sizes, go around the border of here using all tile sizes, go around the border of here using all tile sizes, and go around the border of here using all tile sizes. And when we do that, the underlying data structure, that underlying texture memory that is storing those tile values, if we do that correctly, then visually what we'll get is we'll get this. We'll get this. Now, the next thing we want to do is, yeah, that's great that we have visually confirmed that, but we really want to confirm it. We want to confirm it pragmatically as well, right? We want to be able to run the test, and we don't want to have to like run the test and then open up a file and be like, hey, does that file look right? Like that would be kind of hackish, right? So we want to, now that we have what we're looking for, we want to iterate through all of these pixels, all the pixels that should be white. We want to iterate through them and confirm that pragmatically. So let's see where we are in the code. And we see that this function right here is, it's Atomic Alice 2020, Atomic Alice C code 2020, PAINT5D subsystem 1 OpenGL, unit test code, canvas user pixels, converted to canvas user bits, put. That's a mouthful. So you can kind of see why I use a very terse style, because I don't want to, I want to look at everything in terms of the data transformation that is happening, right? Like every single function is just a transformation of data, right? And because every single function is a transformation of data, the easiest way for me to wrap my head around what is happening is to think of it in data transformation, right? So a lot of people would want to like do something higher level and abstract things higher level, but I think that would just make things more confusing, right? If we came up with some type of user-friendly name for this, I think it would make the code harder to follow, right? Because we have a variable for this, so we know that this is our input variable. We know that C2 stands for convert to, so we're doing some type of transformation to that variable, and that this is the output, and the output is being used as a putter rather than a getter. So to me, this naming convention makes more sense to me. And also, we're being very terse about this because even with the level of terseness we're using, we're being incredibly terse with our code to the point where if you're not well acquainted with the code base, this looks completely cryptic. But even though we're being very terse, this function name is still gigantic, right? So we're using a very terse... Oh, so I see somebody stop by. So if you want to take a look at my technical demos, they're right here. You can take a look at that. I'm taking... most of the things you see in the technical demos are proofs of concepts that I'm going to merge into one cohesive engine, and I am working on a fractal auto-tiling engine. So unless you ask any other questions, I'm going to keep on explaining what I'm explaining here. So yeah, right here, very terse language, but very terse, but also very, but it's still a very long function name, right? But this is how I like to write my functions, just so I can see, here's the data going in, here's the data going out, right? Okay, so now that we're in here, we want to pragmatically assert that we have all of these white pixels in that texture memory, right? Because we have just visually verified that that is correct. Like, I am absolutely 100% certain that this is what is in the data, because I just did a memory dump to a file, right? So now we just gotta iterate over that and verify it, right? So right here, let's see, right here, let's find the color. So how do we know that we're setting all white pixels, right? That could be the first thing here. So this is a location, right? This is the location of the pixel, and these are our bits. So let's highlight this for a second. So this variable right here, right? It's an unsigned 32-bit integer. This is how we know we're setting those white pixels. So if we actually look at what we're setting here, we're setting a cluster of... Ooh, that's actually wrong. Is that wrong? Yeah, so that's actually... I mean, we'll fix it. We'll fix that really quick, but it doesn't create a problem for us, but it's still... I think it's still wrong, right? So let's go over here right now. So we said FF, right? And if we put FF... We have 4 Fs in here, in this code, right? 4 Fs. I make this mistake a lot. So 4 Fs, if we look at the bit twiddling, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, never mind. That's right. Never mind. That's right. So 16 bits, right? It's 16 bits. Like, this is all binary ones, right? And that's why we're getting... that's why we're getting those white pixels. Because we're always going to use this bit payload for specifying the different tile values. And if we use that bit payload and we iterate over all these coordinates, all these locations, and we iterate through all 3 layers, and we iterate through all auto tile sets, then those will all smash together and get the pixel color. How do I say this? Okay, let's not worry about it. This is how we get those colors. Let's just verify it. So after we iterate through everything here, we need to kind of loop through here again and just look at every single pixel. So this dex right here, there's 2,031 pixels that... So let's go to the view right here. So 2,031 pixels. What's that about? So all these white pixels, there's exactly 231 white pixels. And we need to check each one of those and make sure that it's that color, right? So that's why this variable is called dex2031, because there's exactly... sorry, did I say 231? There's actually 232 pixels, but this is the index, right? So it's labeled based on the maximum index. So you see lay 002, that stands for 0 to 2, right? And this stands for 0 to 15, right? So that's kind of the naming convention. Now, if the variable were not an index, if the variable were a size, then I would... then things would be like, would look a little bit different, right? Then we'd have powers of 2 usually. If things are sizes, they're most likely power of 2 variables. If things are indexes, they're usually like off by 1. So they're usually, if they're indexes, they're usually a power of 2 minus 1. But if they're size variables, they're going to be just a strict power of 2. Anyways, so we need to loop through all of this again. We're going to loop through all of this again. And when we loop through it, we need to transform that into a coordinate, right? So this is how we're getting we have this helper function to give us that coordinate. So let's take this coordinate. We don't need to assert that it's correct. We already know this coordinate is going to be correct, right? And once we have this coordinate, we need to confirm that it is the correct value. So if we go in here, the data for that coordinate is actually stored in here. So we can take this and we're going to need to convert the coordinate into a pixel into component indices. So let's take this really quick, and at the beginning of here, we're going to define this as CPU pixels. Right, for the paint, this is the texture memory for the PAINT5D system as it exists on the CPU. So it's the CPU side copy, right? Okay, so we're going to undef this. Okay. And now we can kind of, instead of using this, we can do CPU pix. And we need a component index. We need a component index plus 0. And we just need to assert that we need to check red, green, blue, and alpha, right? So, all channels of the pixel should be confirmed to be all 1 bits, right? So that's what we're kind of doing here. AKA opaque white pixels, right? That's what we're doing here. So let's make a note of that, right? So at vid IID, and we got 105, right? Video 105, and the time is 7 hours, 53 minutes, and 50 seconds, right? So right here, we're going to confirm that every one of those pixels is a white pixel. So we're going to confirm what we have already visually confirmed that this is what's getting set on our texture memory. But now we just want to pragmatically confirm that, right? So that's what this is going to do. Now you might notice that we do not have any variable called comdex here yet, right? Comdex stands for component index. We need to figure out what that is, right? So to get comdex, we need to take, so this is canvas user view IX, canvas user view IY. Now, why the heck do we have this? Is this correct? Okay, let's look at our math here. Hold on, let's look at this for a second. So canvas user view X and Y. Oh, hold on. Well, I guess make this purple. Okay, let's make sure this is correct. So canvas, oh, okay, so our put function is in terms of canvas user view pixels. That's fine. Now the problem is that right now we want to convert the canvas user view pixel locations into we want to convert that into a global pixel coordinate, right? I don't know if we have a function for that. We have paint pix to canvas user view pixels. Hold on, let me put some breakpoints here for a second. Do we have an inverse? So we want this function, but we want it in the, actually we don't want that either. We want like a, we really want a function. Man, like, you know, this cascade's out of control sometimes, where it's like, man, we're right, but then it's like, oh, wait, we need this other transformation to check this. And it just, this spirals out of control pretty fast. So hold on here. So we want to, well, let's see what kind of coordinates we have in here. So this canvas user XY, is that a, we have the index, we have the layer, we have the offset dex. Yeah, we're going to have to... Yeah, we're going to need... Man, this always gets out of control. This always... It's like, you think you have everything, and then one thing leads to another. And here we are, making... spiraling out of control. Okay, so let's look for. So let's first of all let's do a sanity check and be like, okay, well, what do we want? We want the transformation of CuviPix, right? So canvas user view pixels, and we want to convert that to GlockPix. We actually want to convert that to global pixels, right? Global pixels on the canvas, and I guarantee that is not anywhere. So now the thing is that really belongs in that this function, if it were to exist, it really should belong in that would really belong, it would be proper, it would be most proper for it to be in PAINT5D functions, not in the GLSL function stuff. Like, when we're actually gonna, if we ever actually use a function for this, it's going to be on the CPU side. So let's take this, and let's just take it and say, oh, okay, we need to make this function. Okay, so where are we going to put the function? This file is kind of like already out of control. Okay, so info status messages, helper functions. We're gonna kind of put it at the first. So we got more helper functions generic. Helper functions conversion. So would this count as a helper function conversion function? And I think it would, right? So tile exponent to some other things. Tile exponent to maximum coordinate, tile exponent to diagonal pixels, diagonal pixels to tile exponent, deleting some stuff. This is the wrong formula. It is the inverse, delete sometime, preferably after PAINT5D is working. So I'm going to keep to that and say we're not going to delete that yet. Diagonal pixels to ASTPix. Now, what is ASTPix? Because I kind of forget what that is. So hold on. I'm going to put this here. Need this function. I'm just going to throw that in there, so it'll throw an error if I forget about it. ASTPix, I want to make sure that I don't have, that this does not stand for something that I'm already trying to make, right? So if I forget what something stands for, I want to make absolutely sure. So ASTPix means, what does ASTPix mean? ASTPix, offset subtile pixel. Okay, so I may have, that may actually stand for something that I have kind of like made another name for. Right, so that sounds an awful lot like some of the, like PEBTX, PEBTY, doesn't it? That sounds like what that might be. Maybe not. No, PebbleTX, PebbleTY is always in terms of the smallest tile. I think offset subtile pixel X, I don't know. Let's look at that. So, ASTPix, if we look at the calculations here, can it make this function because it's a one-way conversion? Yeah, so let's kind of, I do want to look for this and kind of see what ASTPix is. So let's highlight this. You know, we make up so many concepts, and then sometimes we forget what some of them mean, and then we reinvent them. Offset subtile pixel location. So we know it's inside of an auto tile set, and it's one of those. It's a subpixel, so it's probably some type of local location. And if we look at this, oh, it is, it's a one-dimensional location because ASTPix is the same on the X as it is on the Y, right? Yes. Okay, now do we have a diagram for this? There should be a nice little diagram to explain this. Yeah, diagram, dia selected tile qua, and this is in PAINT5D data. So let's look at that diagram really quick. So in the PAINT5D diagrams, we have an explanation for what that is. So diagpix and ASTPix, where is ASTPix? ASTPix an XY location local to this diagram, local to an offset subtile. Right, it's an XY location. So okay, so it's not really like a PEB-TX. It's not really like PEB-TX, because Pebble-TX, Pebble-TY would be a local coordinate somewhere in here, or a local coordinate somewhere in here, or a local coordinate somewhere in here. Or actually, no, Pebble-TX would not be that. Pebble-TX would be a local coordinate like this, or a local coordinate over here, or a local coordinate in here, but it wouldn't be any local coordinate in here. Pebble-TX would only be here, here, or here. So Astapix is definitely a different concept than PEB-TX, PEB-TY. I just want to make sure, right? Because in case we invent too many concepts, and it's kind of a rarely used concept, and that's why I'm like, whoa, I forget what that means. Okay, that's fine. Let's see what other kind of conversions we have here. Quark map conversions, GlockPix to PAINPix. So these helper functions look like they're more granular, right? So these are conversion functions, and they are kind of generic. They're kind of like very low level, very basic conversions. And so if we look at the code down here, we have something called Quark map conversions. And so if we look at this data here, I kind of sometimes will refer to this MIP map like data structure as a quark map. That's kind of rough, right? It's not always quite correct, but it's roughly, sometimes I refer to this data structure as a quark map, right? Because it's like a quad tree. It's like a quad tree packed into pixels, right? So I just call it a quark map to differentiate it from. It's basically a MIP map that's encoding a quad tree, right? That's basically what we're doing, but I call it a quark map sometimes. Anyway, so if we look at the functions here, we can see that GlockPix to PAINPix, and then we have the inverse, right? We should have the inverse after this. Oh boy, that's a lot of calculations. PAINPix to GlockPix. So we have the inverse right next to it. Quark map, and then we have pixel bit packing. Okay, so I'm gonna say that these that what I want to do is counts as a quark map coordinate conversion, right? I think that is valid. So what we're gonna do is we're gonna put this. We could make a little header right here, like a little index of what's in here. So just say, you know, index and 1, 2, 3, and 4. So we're going to have 4 index items. And we're going to have... So this is... Okay. So GlockPix to PAINPix is right here. And then the other one is down there, right? So if we scroll all the way down here, right, this is the other thing in here. And there's nothing else in this section. It's just a very big... those functions just are kind of big because they have like a lot of asserts in them to make sure that those coordinate calculations are correct. So let's number this. So we're just going to make a little index. We're not going to use any forward declarations. We do not code with forward declarations unless it is a unit test, because we want to have a very strict ordering in our file where we don't have to worry about, if I want to find a certain function, I should just be able to see, oh, it's called here, so therefore it has to be up above in the file, right? If I don't use any forward declarations, I can always find a file and a function because it's always going to be declared above its call site, right? So right here, we're going to say, okay, we need this function, and if we're going to code this function, we might as well code its symmetrical function, right? So AAC 2020. And we did GlockPix to PAINPix, so we should do... So this should be the second one, right? So if we're going to group this in a logical manner, then we want as much kind of similarity as possible. So what do I mean by that? Hold on. So we see that Well, let me just finish this, and then you'll see what I mean here about similarity in the code. Similarity, consistency. We want to be as consistent as possible. Okay. So, if we look at this, we see that... Is that right? Yeah. So let's highlight Glock picks right here. So you see how we have these same diagonals right here, right? So I could have ordered this, I could have put this function first and then this function, but I specifically did this function first and this function first so that it has the most regularity with being similar to this, right? When I'm looking for patterns in the code, I want everything to be as regular as possible, right? So it's not quite the same thing because this is canvas user view pixels, but you see we've kind of coded it so that everything's as similar as possible, right? So, right, so we can make we want to code in a way where we want to accentuate patterns in the code so that the fast-thinking pattern recognition part of your brain can kind of visually lint the code, right? If that makes sense. I don't know if that makes sense, but that's what we're doing. So let's stub in these functions really quick. So everything's out of control because now we got to make more functions, and now technically we need to write tests for this. So much stuff. Okay, so let's stub in this function. Let's stub in the other function. Okay, so same function, well, inverse function, right? Complementary function. Let's put like little section dividers between the functions, right? So we want to be able to know that these are separate. I don't know. This is the way I like to code. I don't know. Okay, so now we have more work for ourselves, right? It's a devil's staircase. We get closer and closer and closer. And then, bam! More functions we need to make. So, man, I need a break. So we're at 8 hours. We're at 8 hours. So, I think it's a good time to... it's a good chunk, right? This is a good chunk. It's a good time to kind of like stop the stream and just do some more push-ups, right? We're going to do some push-ups. And if we look at our push-up counter, right, our push-up counter is at 80. If we do 20 more, then we're at 100, and that's when we jump on the trampoline. It takes a while to get out and jump on the trampoline. So we're at 8 hours. It's a good stopping point to... So here's what I'm going to do. I'm going to stop the stream. I'm going to do my exercise. Probably take me no more than 30 minutes. More like probably 15 minutes. But then I might like heat up my coffee or something. Get some water. Get a snack or something. But I'm gonna stop the stream here. Get my exercise, come back, and then we're gonna figure out what goes in these functions. And then if we really want to be proper, we have to write test code for this stuff. I don't want to write test code for this stuff. We should be able to verify that it's correct. Let's don't write things that we don't need though, right? So this right here, we're taking these we're taking the Kuvi picks, we're converting it to Glock picks. We actually don't need this function here. So error Yagni, don't write it until you need it. So let's not write this. Let's not write this. Now we'll put the correct signature in here, but we're not going to write this one, right? Because if we write this one, we have to write test code for it, and we're going to know we don't need to really write test code for this one because this test function, we've already verified that the texture memory looks correct. So if we can pragmatically verify that the texture memory is correct by using this helper function here, then we will have we'll be like 99% certain that this function is correct. Okay, so let's at least write this code when we get... So we're going to write this code right here when we get back. But what we are going to do with this function but this function, we're going to figure out the signature, right? So if we look at, we want to keep the signature the same as the other code, right? And we notice that we take the paint pixel, and then we get this like global pixel here, right? And then for the signature for this other function, for the complementary function, it's all the variables in the exact same order, except we change what is a pointer and what's not a pointer, right? So all these variables are in the exact same order as the other function, right? So if we go up here, so both conversion functions, same variables, same order. We just change what is a pointer and what's not a pointer, right? So in terms of this, these are output parameters and these are input parameters, and we did that so we didn't have to worry about thinking about what the parameter order was. Like, if we want to use the inverse of this function, all we got to do is swap this variable for that variable in the function name, and we use everything in the exact same order, but these become input parameters, so we get rid of the stars, and then we put stars on these, and then boom, we're done, right? So we just are organizing things so we have the least amount of things we have to remember to get this code working. With that said, well, this object here, all these variables here are conceptually a thing called a paint pixel, and we see here there's no reference to a paint pixel here. So how do we get the most symmetry with these functions to make it most similar to these? Well, since we have glow_tx, glow_ty, and these are the global coordinates, the way we're going to get the most symmetry is if we keep these as the last parameter, right? That's the way we're going to get the most similarity with these functions down here, is if we make these parameters the last parameters, right? We want the code as regular as possible, because the more consistent we can make this code, the less we have to memorize, right? So I see somebody's kind of stopped in, and I know it's kind of annoying, but every time I see somebody kind of stop in, I'm gonna shoot my demos in here so you can take a look at my technical demos. I'm working on a fractal auto-tiling engine. You may have heard this pitch before. All of the things I am putting into this engine are in that technical demos page. And then there's also this, hold on, for Andrew 01 URL. No, for Andrew 01. And then also this is also some technical demo of another aspect of the engine. But right now I am working on some unit test code. I was about to take about a 30-minute break, but before I take a 30-minute break, I am filling out the signatures for both of these conversion functions. Okay, so conceptually, what is a canvas user view pixel? Well, conceptually, a canvas user view pixel, we can see on this screen over on our right that a canvas user view pixel has a canvas user view IX, canvas user view IX. Now, this thing called covbox4 is a canvas user view pixel that has a very specific coordinate, right? So if we look at this data structure here, a canvas user view pixel, well, that's not quite correct. A canvas user view pixel that can map to the data that is white here. If that canvas user view pixel location can map to any of these white pixels, then that canvas user view pixel is also a covbox4 type, right? So, but this covIX, coviY is a canvas user view pixel type. With that, conceptually, so we're trying not to wrap things in extra objects. So I know, like, if you're used to object-oriented programming, you're used to, like, oh, we got way too many parameters, let's wrap things in an object. And we're not going to do that because we don't want to encapsulate our data. We actually want to see what our data looks like, and we want to be able to feel our way around the code very easily. And to do that, we're going to have to expose more things than we would usually expose, right? And you might be like, well, that's kind of weird, that's kind of clunky, but as Mike Acton of Insomniac Games would say, different data, different problem, right? So I don't care about encapsulation, because if it's different data, then it's a different problem, right? And we're coding for a very, very specific problem for a very, very specific engine. So there is no need to like add extra encapsulation, add extra mental indirection, add extra convolution to this system, right? So the canvas user view location, well, what is the range of that data type? Let's think about that for a second. So, because we're in the PAINT5D system, and that does use a properly ranged data type, and if we look at this diagram, the canvas user view pixel is between 0 and 255, which means that we can actually use only 8 bits to address all of this space. We only need 8 bits per axis to address 0 to 255. So we're in this specific file, in this specific function file for PAINT5D, we always target the exact bit width, right? We don't use any more bits than is necessary to address whatever we're addressing. So we're going to take this, and we're just going to say, bam, the canvas user view X, the canvas user view Y, and this is, you know, canvas user view chord. So there's X and Y, right? So X and Y. Okay. Okay, canvas user view X, canvas user view Y, and then we have to just kind of like do a no-op here, right? So we're not actually going to write this, right? Yagni, you aren't going to need it. You aren't going to need it, right? So do not code things that you do not need. Do not code things that you think you might need, right? There's an exception. If the thing you might need is like, you know, maybe like if it takes you 50 seconds to code it, and I mean 50 seconds. Like if you think it's going to take you 50 seconds and it starts taking you a few minutes, stop, okay? But if it takes any more than about 50 seconds to write, Yagni, you aren't going to need it. Unless we actually have a specific call site where this function is actually being called right now in the code base, do not code this, right? Because if we write this, then we have to write a test for it, or we at least have to have it being ran or called in production code. We need some type of certainty that that code is right. So, well, there's two problems, right? We need certainty that the code is correct, and we also need a reason for it, right? We just don't want to waste time, right? Now we are going to stub it in. We are going to waste time stubbing it in, but we're not going to waste time with the body of the function. The reason why we're going to waste time stubbing it in is because it is this is the complementary function to this, right? So we want to put it in the place on the code base where it exists. So that is why we're stubbing it in here. Because if I make this function, there is like probably a 100%, yeah, there's a 100% chance that if I code this, that at some point in time I will, maybe out of curiosity rather than necessity, but at some point I am going to look for the complementary function where this conversion function is swapped on its head. And so since that is the case and I'm going to look for it, I need to at least stub it in to say, yes, I did think about this, but we did not need it at the time, right? So, so I guess in some way I'm lying because it's going to take me more than 30 seconds to put this in, but I'm also explaining a lot of stuff, right? So it would be a little bit shorter for me to stub this in if I wasn't explaining everything, right? So if we're going to take some variable, and then we're just going to do a no-op on it, right? So we're just going to silence the compiler and say, nope, don't give me any warnings because I don't care. So we just need to do this to make sure it compiles. I have some pretty strict compiler settings. You may not have to do something like that if you're writing your own code, but I have very strict compiler settings because the stricter the compiler is, the less ways you shoot yourself in the foot. Right? So the more rigid and strict you are, the less horrible mistakes you're going to make. Anyway, so yeah, that's all we need here. And this right here, right, we're going to take the exact same function signature here, right? So we're just going to paste this in here. Now, this is the output here, right? So that means that this right here is going to be a pointer, and right here, hold on here. Oh, my bad. Glock picks to Covey picks. My bad. My bad. Wrong. The output is here. So when we convert to... So this is what is getting outputted, right? So, and also, because we're returning using an output parameter, we really want to make sure that the signature returns void to avoid confusion, right? Because if we have a getter style function, right, this kind of works as a getter. Both of these functions work as a getter. If we're going to return the value that we want to get via an output parameter, we don't want to be confused by having it return a value, right? Because if it returns a value, it would be a honest mistake. Like I wouldn't be able to blame anyone if they thought, oh, this conversion function returns a value, right? That would not be a stupid mistake to make, and so we don't want to let people make that mistake. So we want to make absolutely sure that the return type here is void. Okay, so with that said, this covPix variable is going to be conceptually these two variables. So this will be the input, and then over here, we're going to keep the parameters in the exact same order, but we're going to change what the output is. So the output here is going to be Glock picks. So the output here is right here. And let's think about, why do we have an int 16 for the global pixel location, right? Like, why is that int 16? So let's look at the diagram here and look at this data layout. So the Glock pix stands for global pixel, and it is a global pixel coordinate somewhere on this data layout. And this data layout is 512 by 512. So if we used 8 bits, we could only go up to 255 in terms of coordinates. So 8 bits is not enough. If we use the next step up from 8 bits is 16 bits, and that's going to give us about 65,000. Well, 65,000 is way more addressing space than we need. Okay, well, if 65,000 is way more addressing space than we need, but that's the next size up from 8 bits, what are we going to do? Well, I guess we could make the most of the situation and say, since we already have more bits than we need, we could cut that in half and still have enough addressing space. So we could cut that in half by using a signed integer, and now we have like 30,000 values worth of addressing space. Still plenty within the 512 by 512 coordinate range we need. But by using a signed integer, we can kind of, if we do any type of integer, if we go like negative accidentally, it's going to be much more noticeable because we'll actually see a negative value versus seeing, like, if we use an unsigned value, we'll just see like a very high value, right? So if we do any calculations that accidentally underflow, we're going to see negatives, and it's just going to be easier to diagnose what's going wrong, right? So we're going to take advantage of those extra bits that we have and say, hey, you know, we can just make these, we can make this 16-bit value signed for free and get more diagnostic information from that, right? So that's what we're gonna do. Okay, so now that we've ranted and we're saying, hey, we got this structure here, right? So everything is in the exact same order, right? So let's make absolutely sure all these parameters are in the same order. So we have all these colors: cyan, orange, yellow, and purple, and also cyan, yellow, orange, and purple. And it's the exact same data types in the exact same order. So we got unsigned 8-bit, then signed 16-bit, unsigned 8-bit, then signed 16-bit. Stars are complementary, so these are the outputs on this function, and then these are the outputs on this function, right? So we have 2 complementary signatures and 2 complementary function names, right? So this function name up here is complementary to this function name down here. So everything looks like it's in good order and ready for us to figure out what the heck needs to go in here. But like I said, We're past 8 hours, so it's a good time for me to stop the stream, get my exercise, and come back in 30 minutes. And if you are viewing this, I'm going to say, if you look at the bottom left-hand side of my screen, so I have a little schedule for Eastern Standard Time. So at 5 a.m. was Don Ho, so you could check him out. I don't know if he's still streaming. Hirosa is probably still streaming. I don't know if I'm pronouncing his name correctly, but he is. He usually goes from 8 a.m. to around 1 p.m. Hence why I'm at 1 p.m. here, because I didn't want to overlap, but I kind of couldn't sleep. So I kind of was like, I'm going to waste time if I just let my gears spin while I'm trying to go to sleep, so might as well just start the day super early. But yeah, so I would, if I were you, I would tune into Hirosa right now. I'm not sure I'm pronouncing that correct. He also does C code, and he is doing I don't know if he's doing just a graphical UI engine in C code. I think he's doing some other stuff as well. I think he's actually making a full game. But one of the subsystems he's working on is a graphical user interface written in C. And that's just personally that's what I know about him, because I hate user interfaces. So it's good that somebody else is doing that kind of code, because I'm eventually going to want to use his code for stuff, right? Like, I'm eventually going to want some type of friendly user interface. And when it comes down to that, I really, if I can help it, I don't want to write my own code for that. So I want to figure out a way to get his code into my code base. But yeah, so anyways, I'm going to stop the stream here. And we will be back in 30 minutes after I get all of my exercise. So later.